proudly welcome Dr. Moshe Banerjee, Anand M. Sarjan Collegiate, Research Professor of Biostatistics and Research Professor of Global Public Health and Director, Global SAT Course, School of Public Health, University of Michigan. Welcome, ma'am. And I also would like to welcome Kiran Tikere, MPA, Director, Student Development and Programs, Office of Global Public Health, University of Michigan, School of Public Health. Welcome.
Thank you.
So we are going to start our program now. Firstly,
I just want to make sure that I can. Good. So before we begin, firstly, everybody welcome. I am from Kolkata, as probably all guessed. So this is like, for me, it's like homecoming. Although I am on a totally like crazy schedule, like a business trip. This is, and Kiran, for her, this is her first time to India. So I am feeling a bit of a pity that I'm not able to kind of showcase our country to her because we have been constantly flying. We have had very little sleep, and I'm kind of doing these workshops like 8 hours a day and standing on the feet and barely kind of trying to keep. And it's sort of hot outside, but nevertheless, it's still a wonderful, wonderful feeling to come to Kolkata, my hometown, where I grew up. I went to school at Patubhavan in Baliganj, and then I also went to, for my bachelor's and master's, I went to the Indian Statistical Institute, ISI Kolkata, before I went from the United States for my doctoral studies. I come back to India like at least twice a year because of personal connection and also for professional reasons. I have a lot of collaboration. So with that, a few housekeeping things. I think Dr. Shurupa and Dr. will tell me that when we will have a break so that I can structure the lecture accordingly. Kiran has a sign-up sheet for everyone. So she will pass it around during the break so that we can collect some data on the attendees. So I understand from both of them that this is a very mixed crowd. There are a lot of students and as well as there are faculty. So you are at varying levels of statistical knowledge. And it's usually kind of a hard task to address both these groups, but I'm going to try my best to do that. So one thing that I will say, and we were just at PGIMER in Chandigarh, and I announced this right at the beginning of the workshop, is that I am a professor who is basically, all my students know I love interaction. I don't like to keep on lecturing just, straight. So I would rather you ask a lot of questions. I want a jumpy classroom, like I don't understand this or what, this is not clear. And let's try to engage in a dialogue, in a conversation, because I think that's how you learn best. So don't let me keep on talking. Please interrupt me. Please ask questions and anything that I can clear as we go along. So what we are going to start with is some very basic introduction to statistical methods and sort of some fundamental issues related to statistical inference. And then I was talking to Dr. Shurupa and Dr. Kaushik, and I think we are going to be, depending on the vibes of the classroom and how you are sort of, how you want to learn, what you want to learn, we will customize, if that's okay. I mean, I'll let you decide and we'll go from there. Okay? with that, the agenda, as course introductions, course objectives, I already mentioned that. Today we are going to do a very basic introduction to biostatistics. Tomorrow, the plan is to talk about categorical data analysis, and all through we will focus on concepts, interpretation, alongside statistical rigor. I believe statistical rigor is very important, but for this course, we are going to focus on the concepts, on interpreting results from when you are picking up a journal article to read or critique, to understand. So that would be the focus of this course. So what is biostatistics? If you ask Google, Google will say that biostatistics in effect is two words and two fields of study combined. The bio part involves biology and the study of living things, and the statistics part involves the accumulation, tracking, analysis, and application of data. So biostatistics is the use of statistics, procedures, and analysis in health, medicine, healthcare settings. So now biostatistics as a field has evolved rapidly, and over the last few years, as many of you know, the emergence of data science and big data computing power that we have has rapidly changed the world of biostatistics, how we do statistics now. I trained at ISI, one of the premier institutions of statistics in the world, but my training was very, very theoretical. It was very mathematical. Before I went to the United States, I could prove lots of theorems about linear models, but I couldn't fit linear model to data. I was so afraid of touching data. As a field, biostatistics has kind of shifted like hugely from that notion of being a kind of a branch of mathematics to where now we were at the forefront of COVID modeling, data science, being spokesperson. I was actually called on the national television in India about COVID data and the data that was coming out, and what kind of policy implications it had, and many of us were involved in the pandemic modeling. So statisticians have sort of as a field we have evolved. Now there's a lot of focus. Not only do you have to be like strong in mathematics, in foundations of statistics, but you have to be very strong in computing. You have to understand data. You have to understand biology. Because if you don't understand the biological basis of the study you are involved in, then you might give the right answer to a very wrong question. So we, as biostatisticians, so my work primarily has been in the area of cancer and pediatric heart disease. So I had to understand the molecular basis of cancer. I had to understand Pete's cardiology. So again, the reason I'm saying all of this is that it's a very, very dynamic collaborative field. So why are you here today? I told you why, the field of biostatistics has rapidly evolved. But what about you? Why should you care? The reason you should care is because statistical literacy is not only becoming a requirement, has become a requirement for clinical research. Medical research machinery is becoming increasingly reliant on statistical methodology. Like you pick up any journal article, starting from the top tier medical journals like New England Journal of Medicine or Journal of American Medical Association to your subspecialty journals. Each and every published study, to understand it, interpret it, critique it, requires a certain level of statistical understanding and statistical literacy. So that's why you are here today, so that you are able to understand medical and public health findings. and make informed individual and broader level decision making, guided by proper understanding of data and published findings. Medical questions that like you deal with every day, probably in your practice, you would be surprised that so many of these questions have their fundamental basis. They are statistical in nature. For example, what's the diagnosis? How accurate is it? When you ask this question for us, statisticians who do evidence-based research, we are saying that can we actually come up with an accuracy measure of a certain screening test? Okay, so how do we, so there is behind the scenes, there is statistical modeling. What about, what are my chances, doc? This is probably the most fundamental question that any physician has to encounter. And how many, I don't know how many of you realize, but back behind this sense is a complicated statistical model that actually calculates your probability or your risk of, having cancer recurrence or, dying of certain diseases. Although I'm guessing all of you here are involved in pediatric research, but there are many risk models in the clinical literature that have a basis in statistics. For example, in breast cancer, there is a model called Gale model, GAIL Gale. Gale model was developed by Mitchell Gale at the National Cancer Institute in the US. He is an MD, but he also has a PhD in biostatistics. And Gale model, essentially, you can capture it in a calculator where you put in, if you put in sort of the woman's age, family history, age at menarche, how many live births the person had, the calculator will give you a risk estimate, a lifetime risk of having breast cancer. Now, is that magic? No. Behind what that calculator gives you is a statistical model that was developed on sort of data from many patients. So all of this, is this new drug better than the one commonly in use? Standard clinical trial is trying to address that. And there are statisticians are involved in clinical trial research design. How much better? What are the risks of side effects? How many patients must be treated and in what manner to demonstrate its worth? This is the sort of $1 million sample size question. What sample size do I need to have such and such power? So the point of this slide is that I'm trying to make is a lot of the questions that you ask as practicing physicians are statistical in nature. They have behind the scenes some sort of statistical reasoning. So I'm going to start with the fundamental chain of scientific reasoning. So we have, there's a population that you are trying to understand some aspect of the population. Let's say you want to understand whether BMI is related to HDL. Okay, so that you want to study in the population the association between BMI and HDL. Now, of course, if we had infinite resources, then we would do a census of the population, but that's not possible. So what we do is we draw a random sample from the population, and based on the sample, we try to make some inference about the population. So there is a, from the samples, there is a statistical sampling scheme you use from the target population, and then using fundamentals of statistics and statistical inference, you try to make inference, conclusions about the population based on the sample at hand. So that's the chain of scientific reasoning. In order to make inference about the target population from the sample, we rely on statistical sampling methods, draw a probability sample from the target population, and then apply our results to a population beyond our target population, this is what requires the use of scientific generalization, which relies on knowledge of the similarities of the target and the general population. So what do I mean by the target and the general population? Suppose you want to sort of make some inference about, I don't know, quality of care metrics in pediatric disease. But you are only in India. But you are, let's say, only doing single institution studies, like, you are using data from ICH. So you do your study, that's your target population. You draw random samples from the ICH patient database and you make inference, and that is what you are saying about the ICH population. Then the next question that naturally comes, well, I'm not just interested in ICH, I'm interested in making inference about the pediatric population in India. So can I generalize? Is ICH more or less a representative kind of center of pediatric research in India? And those questions become very important. So how do we make inference? Of course, without data, you cannot bring data like our sort of data is like clay. Without data, I love this quote from Sherlock Holmes. Data, 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 he cried impatiently. I can't make bricks without clay. So for us, data is the clay. And in order to, or you can say data are the bricks, and in order to build a house, you need bricks. So same here. So these data is the essential or critical component of or the building block of statistics. So when we talk about data, and this is very basic, when we talk about data, essentially statisticians like to talk about data as variables. BMI, LDL, gender, race, ethnicity, eye color. To us, these are variables. Okay? Why variables? Because each person in the sample could have a different value of that variable. But when we are talking about variables, one thing that is very important is the scale of the variable. What do I mean by the scale of the variable? The measurement scale. For example, most of the, or more commonly, the variables we deal with are continuous, like age, BMI. These are continuous variables, or sometimes what are referred to as ratio or interval scaled variables. What about variables like gender, race, ethnicity, education, like level of education? These are categorical variables. Categorical variables also could be of two different kinds, nominal versus ordinal. What is nominal? Nominal means the categories per se do not have any ordinality, any ordering. Like eye color, brown, black, blue, there you cannot order. You cannot say 1, 2, 3, right? Or hair color, or race, ethnicity. However, if you're talking about cancer stage, localized, regional, distant stage, although it's categorical, there's an inherent ordinality. Distant stage is much worse when it comes to prognosis than regional or local stage. So these are the different types of measurement scale that essentially determines the nature of the analysis. So I'm going to kind of give you a bit of a sort of preview of what we will talk tomorrow. And the reason why I want to put this into context is you might say, well, why do we care? Why do we care about the measurement scales? The reason we care about the measurement scale is because that determines the framework for analysis. All of you or most of you have heard about linear regression. Linear regression is the bread and butter model for statisticians when the outcome variable, what you are trying to predict, is a continuous variable. Like for example, LDL. You are trying to understand the association between BMI and LDL or predict LDL from BMI. So LDL is your outcome, what is on the left hand side of the equation, and on the right hand side of the equation you have BMI. So for a linear regression model, that left hand side of the equation has to be continuous, like LDL. What about a cancer stage or grade of toxicity, or even like take the simple example. Does this person have disease or no disease? Cancer, no cancer. I want to predict the risk of having lung cancer even a person was smoker. Okay, so very fundamental question. I mean, we already know the answer. Okay, tons and tons of published literature. But let's say we are trying to predict the risk of lung cancer based on smoking, family history, age, and so on. So now, cancer or no cancer becomes your outcome variable. Why? Because that's what you are trying to predict. And cancer, no cancer, this is what? This is a binary variable, yes, no, 0, 1. Why is it important to make the distinction between a continuous and a binary variable like this? Is because now to model the risk of lung cancer as a function of, actually I'll take one key. Can I take one key? Yeah, that's fine. To predict that, basically what will happen is now the regression framework will be different. It's a logistic regression framework. Maybe for a section of the audience here, I might be jumping a little bit, but I just want to give you the big picture as to, every step of the way when I'm talking, question yourself, why should I care to learn this? Why am I spending like 4 hours in a classroom? I have a very busy schedule. I have lots of patients to see. And then you should ask yourself this question, why, at every step. And the reason why is because the sort of the framework changes, the regression framework changes. The other kind of data you probably deal with is what we call time to event data, time to death, time to recurrence of certain disease. That is a very special type of modeling framework. So we call those sensor data, because for everybody who you are following, not everyone may have developed recurrence, not everyone may have died by the end of the follow-up. So that's what we call sensory. And the time to event data, the regression framework for time to event data is called like a proportional hazards regression, a Cox model. And again, it's extremely popular in the clinical biomedical literature. So the scale of measurement determines the regression framework. So that's why you have to understand the measurement scale. Okay, and what about the summary statistics for these variables? So like a continuous variable typically is summarized using mean, median, etc., range. For a nominal or an ordinal categorical variable, often we look at the frequency counts. What percentage of the population has disease? What percentage of the population are daily smokers? What percentage of the population takes statins, for example? So these are essentially what we call categorical variables. The next thing that I'm going to talk about, thank you, are are some exploratory data analysis techniques. So typically, this is a very basic rudimentary summary. So a bar graph or a histogram is what we will see later. So here is a bar graph of showing the distribution of a certain variable by gender, males and females. Essentially, what it does is it creates a rectangular display with the frequency or the relative frequency as your y-axis. On the right-hand side panel, I have a plot which shows the kind of the y versus x sort of depiction. Often, these kind of plots are very useful or fundamental to trying to understand bivariate association. So association between two variables, let's say BMI and LDL, although the units are not for BMI LDL. But this plot is referred to as, how many people know what the name of this plot is? Scatter plot. Everybody knows. Okay, so this is a scatter plot of y versus x. Why is that important? Because even before you run a regression model, you can look at the scatter plot and what strikes out of that scatter plot. What is the pattern? Linear. Okay, there seems like there's a linear association. What else? Positive association, meaning as x increases, y also increases. What else? Say it again.
X equals to y. This is implying it can be x equals to y. After can be near about 1 because the data points are showing very linear.
Okay, so how many people agree with that statement and how many people partially agree, fully agree, or don't agree with that? Sorry, in America, it's not the culture that you call students to whiteboards and tell them or ask them questions. But in India, that's very prevalent. Even after being in the US for 30 years, I still retain that style. So I'm going to ask. I'm going to ask questions. If you are not asking me questions, I will. So how many people agree with that statement completely? He made 3 points. One is that it goes through the origin. So the other point you made was the R square would be nearly 1, right? Or there was a third point you made, but I forgot. Or were those the two? Those were the two. So how many people agree fully with that statement? And how many people agree partially, or how many people fully disagree? Partially agree. Partially agree. Okay, great. So what do you agree on? And what do you disagree?
Whether x is equal to y will be dependent on the slope of the line. So
Okay.
if its slope is 45 degree, then x will be equal to y.
Okay.
If it is not that, then it may be less of.
No, scale of x and y are different.
Yeah.
So one may not coordinate with one of y may not coordinate with one of x. So x is definitely not. It's not totally linear. There are ups and downs.
Okay. Okay. So, so this is, I'm going to take that comment and make this interesting one. So yes, like from this plot, if you don't pay attention to the scales, there is some sort of evidence that you might get a slope close to 1, like a 45-degree line, right? But as you can see from the scatter, as the point you made, that all the points don't align exactly on the 45 degree. There is sort of variation around that 45-degree line. And this is what we call statisticians' random error. We usually write it in a model as an epsilon. Random error, what is random error? This is what nature throws in to mess things up. And statisticians, we operate in under that error So if this were a perfectly like deterministic relationship, like the temperatures in centigrade and Fahrenheit. If you give me the temperature in centigrade, I can tell you exactly without any error what the temperature in Fahrenheit is, because C over 5 is equal to F minus 30 over 9. But statisticians don't deal with those kind of equations, because for us there is a plus epsilon, a random error. So if somebody gives you BMI, you can only predict LDL. You won't be able to give a value of LDL with 100% accuracy for everyone, right? So that's what we call random error, and that's what makes life spicier for us. And I think that's what keeps our job. Because we are dealing under uncertainty, under chance variation, how do you make the best, or how do you interpret best the relationship between Y and X? Okay, so that's why partially is a good way to put it. The other statement you made is it's related, that you think that R squared will be 1 or very near 1. I would disagree with that, because again for that random error, because like what is R squared? R squared, we will see later, is the percent of the total variation that is explained by X here. Again, there will be certain points that you can predict with high accuracy, but there will also be points that where you will be off. Okay, so again, the main point of this plot is that there is variation. There is variation around the average relationship between Y and X. So another kind of, plot that, again, these are all purposely not labeled axis, because I kind of wanted you to take a guess. So the third plot here, on the y-axis I have probability 0, 0.2, 0.4, 0.6, 0.81, and on the x-axis you can think of it as like a time variable. 0, 2 months, 4 months, 6 months, 8 months, 10 months. People who read a clinical literature a lot, this kind of graph should look familiar. Anybody wants to take a guess? Exactly. So this is a time to event kind of data. So time to, let's say, cancer recurrence, time to death, time to like from diagnosis to definitive treatment. On the x-axis, I have the months. On the y-axis, I have the probability. So let's say if I'm looking at the time to recurrence, then what this graph is telling me is for the blue line at 2 months after diagnosis, the chance of recurrence is roughly about 0.7, right? But for the red line, it's roughly about 0.87 or 85. So that's another type of plot that is used to understand time to event data. So what's the natural kind of sequence in which you should start any analysis? So start any analysis with summary statistics and plots. Why? This is a very important step that often is ignored or overlooked, and people say, well, and again, I see this all the time, not only in my students, in my own students, that they sort of are prone to 5 minutes into meeting with a clinical collaborator, they want to jump and write a model and sort of work out the math, because they come from that background, but they often don't look at the summary statistics, the plots. And why is that important? Because you can check for errors and anomalies, you can check the distribution of each variable, you can check the frequencies of the categorical variables. There are sometimes very small frequencies, as you will see, like tomorrow, that if there is a certain kind of variable with that has multiple categories and then some categories are really rare. For example, if I'm doing a study here and I am looking at race ethnicity. So, predominantly it will be one class. I mean, if I'm doing a study in the US, it predominantly there will be Caucasians and then some African Americans, a few Asians, but very, very few maybe are relatively few, at least in Ann Arbor, will be sort of like original African origin. And so there might be categories that are very small. And so if there are frequencies like that, you may need to pull it with other categories, and you may need to of math kicks in and we can solve and get an equation for the best. I digress, but I think these are great questions and please keep them in mind because I think that's how we learn best. Does that make sense? So that's why I asked you, yes, you can kind of do a line through one, but how do you know that's the best line? The way you know the best line is, so there is a theoretical underpinning, like how you come up with that best line. So many of you maybe in some softwares when you are running your regression model and you think, you give the data and it sort of gives you the best regression equation to predict. It's not magic, it's not voodoo. There's a lot of behind the scenes mathematical reasoning as why that's the best line. And it's essentially. Okay. So basically the sequence of biostatistical investigations is you design an experiment or study to collect information on a set of individuals from the target population to address a set of issues or hypotheses. And these are mostly, there are two different types of broad classes of study. One are randomized experiments and then observational studies. I have a section where we talk about different study designs. We'll see if we, kind of want to go into that. But let's just take a minute to say again why it is important to understand study design. The reason why it's important is because in a controlled setting, in a randomized controlled trial, you can actually control for a lot of extraneous variables. Let's say again, give me an example. Something like you are running a clinical trial on, and you give a certain kind of intervention or a drug to one group of patients and to another group of patients. Let's say you give a placebo, okay? And you want to see if there is a treatment effect, a drug effect. So now in a controlled experiment, what you do have the advantage of is that you can do the assignment of drug versus placebo in a way where it balances out the groups in terms of other things that could affect response. Say age, say gender, say other comorbidities. So you could assign the drug versus placebo in a sort of stratified random sampling type of scenario where within each age group you randomize, within each gender you randomize. So you are making the playing field same between the drug group, the intervention group, and the placebo group. Why do you need to do that? Because you are saying, well, I'm going to now assume that any difference that I see in the outcome between these two groups is due to the drug and drug only. I have made everything else same between the drug group and the placebo group. So that's the advantage of a randomized design. You can control. A lot of us statisticians deal with observational studies, data from like population-based registry, from electronic health records, where you basically don't have any way of handling who gets what. You just observe. It is what it is. And observational. So my work is primarily in the field of observational studies. I work with big cancer registries, big pediatric cardiac critical care registries from multi-institutions, where basically the issues with observational data is there are lots of confounding, lots of things that you have no control on, missing data, attrition meaning you lose people to follow up. But the most key nightmare for statisticians working in observational settings, data settings, is confounding. And confounding can severely, thank you so much, confounding can severely bias your results. What is confounding? Again, I'm doing a little bit of digression. What is confounding? Suppose again, LDL and BMI. Okay, that is your primary focus to understand the association. But age may confound BMI. Meaning what? So there's a third factor here, say age, that has an effect on outcome that is also related to BMI. And so, how BMI impacts LDL can be sort of determined by age. Another way of looking at it, if you ran a regression of LDL with BMI, you got a slope. Okay, for every 1 unit increase in BMI, LDL goes up by X, like some amount. That's the interpretation of slope in a regression model. Now you bring in age in the model or gender in the model, and the slope for BMI changes, like or even as much as that now it becomes statistically non-significant. Then what it's saying is that, well, you know, age and gender in a way are confounding the relationship between BMI and LDL. So in observational studies, that's just like rampant. And when dealing with observational studies, you have to be very cognizant of biases, confounding, because those would throw your inference haywire and you might be making wrong conclusions. So the type of modeling that observational data scientists do is quite different from what people would care about in randomized trials. Explore the data by computing graphical and numerical summaries. This is what we talked about, numerical measures to quantify central tendency, spread and shape, and this coming up. And then graphical summaries to study the distributions and associations. And then the third thing, or the most important piece, is the inference part. Because we want to translate these findings into inference about the target population. So what is statistical inference? Statistical inference can be broadly classified into estimation and hypothesis testing. Estimation means you try to obtain an estimate of the slope, confidence interval for the slope. And then hypothesis testing is you are saying, well, is there a significant association between BMI and LDL? Meaning that is the slope coefficient beta, is it 0 or is it non-zero? Because if it's 0, then we are saying that, you know, there's no association. If it's non-zero, then there is a significant association between BMI and LDL. So that's what is called statistical hypothesis testing. So how do you use data to actually determine if you would reject the null hypothesis that there is no association, or if you would accept the null hypothesis and say that truly there is no association. So that's what statistical inference is all about. Population and sample, I kind of talked about this a little, but as researchers, we are interested in finding results that apply to an entire population of people. That's what we are ultimately, as you know, kind of our objective is. But we collect data from a representative subset of the population known as sample, and these we use to infer things about the population as a whole. Data is collected in the form of variables, as you saw, like there's different scales of variables. So, so carrying on with the variable, we saw that essentially it's a measured or counted quantity. For example, characteristic of the unit of observation. The unit of observation could be a person, could be a organization, could be provider. Often in studies of healthcare access and delivery, the unit of observation may be the patient. But I also collect information about providers like you treat those patients or hospitals in which you are treating those. So that sort of helps me collect information at various levels of observation: patient, provider, hospital, region, and oftentimes we are interested in the study of healthcare delivery to understand where is the maximum variable. Is it about the patient or is it about the provider who treats the patient? And we collect information on providers like you, your age, your gender, your sort of when you completed medical training, where you practice, all of that stuff. Because there is plenty of literature which says that the practice setting has a on outcomes. So at different levels. As statisticians, we see each variable has a associated probability distribution. What is probability distribution? Probability distribution is a mathematical rule that defines how likely the given values of the random variable are. For example, statisticians love a distribution called the normal distribution. All have heard about the normal distribution. It's a bell-shaped curve, height, weight, all are sort of examples of normal distribution. And the normal distribution is characterized by two things: the mean and the variance. The mean is mu, and the variance is sigma squared. This is a classic example of what we call a continuous distribution, meaning you observe like the space in which the variable can take values ranges from negative infinity to positive infinity. Although height, weight, you don't utilize that entire real line, but it is considered a normal distribution in a constrained space. There are other kinds of random variables that are probability distributions, for example, discrete distributions. And let's see how these again are different. So some examples of discrete random variables: binary, like disease, no disease, toss of a coin, head or tail. So for a disease, no disease, the probability distribution, we call it like a binary, Bernoulli binomial type of distribution. The probability of disease is the disease prevalence in the population. And again, remember I said the reason you need to care about it, know it, is because this defines the kind of modeling framework. What is the modeling framework for a binary outcome? Disease, no disease, it's logistic regression. So no longer can you use a normal distribution, although we love normal distribution, but no longer can you use a normal distribution to model a binary outcome data. So the distribution we use there is a binomial distribution that gives rise to logistic regression. What about count data? For example, you are interested in estimating the incidence of malaria in a certain county. So you are counting the number of malaria cases in a certain county. So there, the distribution that we use is called Poisson, 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 and the probability distribution is governed by a mathematical expression that arises from the Poisson distribution. When you model count data like number of malaria cases, number of cancer cases, incidence of a certain disease, then the regression framework setting you use is called a Poisson regression. Again, a normal distribution will not be valid there. So if you say, well, I'm going to treat the count data as a normal and run a linear regression model, no, you are going to get very biased results. So that's a different class of models called Poisson regression. Examples of continuous random variables, I said normal distribution is our most beloved sort of probability distribution, heights of US population. The probability distribution is a mathematical expression that parameterizes the beloved bell-shaped curve. this is under the normal distribution, the bread and butter of regression models is based. This is called linear regression, and I taught linear regression in PGR and MER just recently this weekend, like 8-hour module. And I sort of started by saying the reason why you want to learn linear regression first before anything else is because it's like the mother and father of all regression models. So first you need to understand the fundamentals of linear regression before you can talk about logistic regression, Poisson regression, or anything else. The other kind of continuous random variable is an exponential distribution. It takes only positive values, for example, life of a light bulb, waiting time until an event occurs, and the type of regression models there is Cox regression. It's a very specialized kind of regression model for time to event data. Lots of mathematical nuances, but again, it's one topic that we offer in our advanced workshop that deals with this Cox regression. Yes.
Run the linear regression, we have to check what distribution it is. It's not-
Yes. Yes. So the answer is yes and no. So you first you can do all those histograms, scatter plots, and all of that to get a sense whether the distribution is fairly normal, skewed, or not. Second thing is you can also do with post hoc, meaning you run a regression model, and the linear regression model comes with certain underlying assumptions. One of the fundamental assumptions we make is that the errors are normal. At the end of the model fitting, then you can do checks to make sure that your assumptions in the first place were valid. And you do it through the residuals of the model. So there's a whole section on residual diagnostics where you use the residuals from a linear regression model to assess that in the first place whether a normal distribution assumption was valid or not. So if it turns out that there is reason to believe that it was not a valid assumption to make, then you look at what other ways, corrective ways could you have modeled it. So there's a whole body of. Now you might be asking about that I should take assumptions upfront. So a lot of times what happens is like if you have like a disease, no disease type of outcome, binary outcome, you wouldn't even entertain linear regression, right? You will go right away to logistic regression. But there may be other types of continuous outcomes that are skewed. For example, cost. Cost is a very classic example. Like cost of a very skewed, oftentimes. So you might be able to fit a linear regression model, and then you look at residual diagnostics and you see, oh, well, I think so much for my cost data, the assumption of normality does not hold. So within the linear regression framework, there are ways you can make corrective adjustments. For example, I don't know how many of you work with cost data. One of the things that is done to sort of normalize it, take a logarithm, natural logarithm transform. So what I'm trying to tell you, the answer to your question is, do I have to do it before? And the answer is yes, partly, but also no, because you can do a lot of things even small. And post hoc within the context of linear regression, because the linear regression model is not only the mother and father of all regression models, but it's a very robust framework. So although it has all these specified assumptions, it is generally quite flexible, even under slight departures from those assumptions, from the normality, from assumptions. And so you can do a lot within the linear regression framework, tweak things here and there, take transformations, do other kind of corrective things, and still fit a linear regression model to something like a skewed variable like cost data. So oftentimes it's a combination of both. Both pre-hoc, like both a priori sort of exploratory analysis as well as post hoc residual diagnosis. Any other questions?
So ma'am, like suppose if I'm using a software like SPSS, I didn't know this part that we cannot do linear regression. It's not a normal. So suppose I have a set of data. It's not normally distributed. I just ran some tests for checking the normality and I found that it's not normally distributed. So in that case, what should I do next? Like what options will HPS give me so that I can do a linear regression or any kind of regression?
Okay, so can I give you a sort of a short answer and a long answer? Because I deeply believe in the long answer. So this is where I think where a workshop like this helps. And my objective and or my philosophy is I'm not here to tell you how to do it. Like I'm not here to tell you, well, how do I do this in SPSS or how do I do that or how do I do that? I'm here to tell you why you should or why you should not do it. Or when you read a journal article, what is it that is done correctly or done well, the design and analysis, and what is it that was done poorly, so you are very much going to be taking or you are not going to be very confident about the conclusions. We all know that there are lots of papers get published in medical journals. Are all of them well done? No. Some of them are so garbage that wonder how they get published. So I am here to tell you why you should do this. And that's sort of the kind of my philosophical answer. And trying now, like a short answer to your question. So SPSS will not tell you what to do next. You have to know, you have from the understanding of the methodology or why you should do the next thing from an understanding from a course like this. Because we all know for softwares, any software, garbage in, garbage out. And SPSS, SAS, R do crazy things that are nonsensical, but they will do it. The question is, do they make sense? And I would say no. I mean, I can give you tons of examples like that. So it's not like SPSS will tell you what to do next. And again, we can sort of talk about customize it a little bit. So basically, what I'm trying to tell you is you as the modeler, or not just, I'm not putting the entire onus on you as the modeler or you as the researcher, you sort of attain that level of statistical literacy where you see the results and you say, well, you know what, I think I need to talk to a statistician. Even that learning is important. That this is where I understand this part. I could run a regression model because I have acquired enough knowledge to understand that I could fit a model like this. But then I also have acquired enough knowledge, Moushumi told me that, I have to look at residual diagnostics, and now I'm looking at residual diagnostics, and I'm thinking that normality is not valid. So what do? I don't know what do I do next. So maybe I should talk to a statistician. Even acquiring that knowledge, I think, is far more important than how do I do this in SPSS. Does that make sense? I don't want to be sounding arrogant, but I really in that philosophy because that is what ultimately helps. And the reason I think why, with due respect, like I trained at ISI, like one of the best, I said, absolutely outstanding training. But I think statistics, the way it is taught in India and in a lot of Asian countries is as a branch of mathematics, and it's not taught in a way where it is really an applied science. and to sort of conceptually understand. It's not that t-test is not a magic. It's not a, and you don't have to understand the math behind it, but I think there's a lot of conceptual things that you can bring into your research, and that's why it's a pity that statistics is, I'm going to be honest, it's not in a kind of a boring way. And that's why probably you all lose interest and you think like, I don't need it. But actually, statistical thinking is a very different sort of mindset. And you all are so accomplished. You are kind of like accomplished in your own work, in your own research. I bet Dr. Sinha, right? Dr. Sinha was saying that you were saying that you have spent a lot of money. এক লাখের বেশি on trying to learn statistics. He feels that he still wastes money. But I can tell you, I think Dr. Sinha, you have the powerhouse of statistical sort of how do I say, intuition, if you were taught the right. It's the thinking. And a lot of people have this misconception that, well, you just press this button in SPSS or this option and it will do it for you. No. And truly garbage in is garbage out. So first, the big thing is that I made it a very long answer because I am very I deeply feel this, that and like, as I said, I have deep respect for all of you, for what you do. So first, let's try to understand why you should be doing it. You could question yourself all the time. That, I mean, why am I spending time here? Unless I can convince you that, and again, you all were asking also great question. So let's try to understand that. Okay, I did not want to sort of discourage you, but I think that's what ultimately it is. Even as I said, even kind of acquiring that maturity that this is where maybe what I learned, my limit is up to that, but I also learned that I need to be concerned about what the results are showing, and to let me consult with the statistician. Okay. So some basic, again, graphical, some descriptions of data, graphical, histogram, box plot, QQ plot, and then some numeric descriptions to these different measures of location spread and frequency counts. So I'm going to very quickly go through this because I wasn't sure like about sort of the mix of this group, and so if you all know this, we don't even have to talk about it. But histogram is essentially, it gives the frequency with which values or of the variable occur. Here is data from Western Collaborative Study, and we have a large epidemiological study that was designed to investigate the association between type A behavior pattern and coronary heart disease. And here's a histogram that was published in a paper by Rosenman et al. In 1964. So again, as you can see, it sort of gives the frequency with which values of the variable occur. So here's the histogram of systolic blood pressure. There are lots of things about a histogram, like the bin width, how should you sort of construct the width of each of these bins, of these boxes, and things like that. But generally, looking at this histogram, what impression does it give? That it looks like a slightly skewed bin, right? So that's all you are trying to gather from exploratory graphical displays like this. Box plot is another. Yeah, it's the density. So it's sort of, it's a relative frequency type of Okay, so now a box plot is another convenient way of graphically depicting groups of numerical data through some summary measures. So it's usually depicted with a sort of a large box in the center, which the line here that goes through the middle of the box is the median, and the top and the bottom of the boxes are essentially the upper and the lower quartiles. Also gives you the largest and the smallest observation once again, and then the series of dots here are what are called outliers, which are outside there are different ways, different software calculate the outliers, like if there are values are in the 7.5th percentile or above of the highest value, or lower than the 2.5th percentile, then they are flagged as outliers. But that's not the point. The main point is this sort of the box, how fat it is or how sort of narrow it is. And the two straight lines, these are also referred to as whiskers of the box plot. So the point here again, you don't evaluate box plot one at a time. You kind of evaluate box plot side by side of certain variables. So it tells you about the spread of the variable. Can you please clarify this? Yes, clarify the upper quartile is that the upper quartile is this one. The upper quartile is this one, and the lower quartile is this one, and this is the median. Okay. What are those? The whiskers? Yeah, the whiskers go from the upper quartile to 1.5 of the interquartile range. So these are sort of extending the distribution of the data based on how extreme or in the upper and the lower quartile. The third one, how many people have heard about the QQ plot? No? So QQ plot is also quite, it's an interesting plot, and mostly it is used to check, again, you were asking about the normal. Someone was asking, you were asking about how do I know it's normal. So QQ plot is a plot that is very frequently used to assess if a certain distribution follows a reference distribution. Reference distribution, in this case, let's say it's normal. I want to see, I have collected data on a group of individuals, let's say their heights. I want to see if the height random variable behaves more like a normal distribution. Let's say that's my question. So what you do is you actually take the heights in your sample, you order them from smallest to highest, and let's say you have a sample of size 50. So you have 50 height values, you order them from smallest to highest, and then you say, well, if they truly were normally distributed, then if I could draw a random sample from a theoretical normal distribution and again order those numbers from smallest to highest, then these two pairs of ordered numbers, the ordered height and the ordered theoretical normal, they should sort of align nicely. So if I plot one against the other, I should get a straight line. Conceptually, does that make sense? It's a very simple kind of, does that make sense? I'll say, yes, of course I'll repeat. So what it's saying is that, say I told all of you, each of you, to go collect data on heights of teenage girls in Kolkata. Okay, so, and maybe the same schools nearby. So each of you go and collect a sample of size 50 of the heights of teenage girls. Okay. Now, I sort of said I'll send each of you. But and that we'll reserve it for later. But let's say now I take the sample, you bring back. And there were 29 other people who kind of had their samples. So now I'm saying that let's check that your sample, does it more or less follow a normal distribution? So what I tell you is now order your height values from the smallest to the largest. Okay? If it were truly coming from a normal distribution, there's a theoretical normal distribution. We know it's a bell-shaped curve. So what I'm going to do is from that theoretical normal distribution, I'm going to draw a random sample of size 50. 50 is how many you collected height on. I'm going to draw a random sample of size 50. I get some values. I order those values again from smallest to highest. Now my rationale is if your sample really came from a normal distribution and I have ordered them, it's a sample of size 50 and the theoretical normal also I obtained a sample of size 50 from the theoretical normal, I ordered them. Now if I plot these two sets on the y and x-axis of a graph, if your sample is truly normal, I should look like a straight line. Yes, everybody conceptually agrees that that's what it should be. And that's basically what the QQ plot does. It's a quantile plot. So a quantile from your sample, if it were normal, then should behave like that corresponding quantile from a theoretical normal. That's the whole idea of a QQ plot. So here, if you draw that line, and if it is like a textbook normal, truly normal, then all the points should align on this straight line, bold line. But here you see that this distribution, again, this is systolic blood pressure. This distribution, this plot looks somewhat like a, well, it's sort of on the line, but there is kind of two little spots, like on the two ends. I don't know if that's whatever it is, like two little bends. So then it helps you decide if the distribution is skewed, if it's symmetric or it's heavy-tailed. Sometimes the plots can look like this. For example, if you have a plot like this, you know, it is still sort of, the reference is again the straight line. And if your QQ plot looks something like this, can you see my cursor? Then essentially it's saying that it's a heavy-tailed distribution. It is still bell-shaped, but the tails are much fatter than what a normal distribution is like. If, on the other hand, if the plot looks like this, then again it is symmetric, but the tails are much lighter than what a normal is. If it is truly a normal, then it should align along that solid straight line. Okay, so now you might say, gee, I mean, you know, this sounds like you are pulling things out of a hat. But again, there's a math. There's math behind it that says why the shape would look like this if the tails are heavy or light. But that's the essence of a QQ plot. A QQ plot is to, and you can change the normal distribution to any other distribution as long as you take the quantiles from that distribution to assess if your sample came from a certain reference. Okay, and these are again, any software can do it, but the idea is for you, I would like you to understand what each of these mean. Why are you looking at a straight line? Why do you want to see a straight line in this pattern? And that's because you are aligning the quantiles of your sample to the quantiles of a normal distribution. So Some examples, here is a negative skew distribution, elongated tail at the left, more data in the left tail than would be expected in a normal distribution. There's positive skew is on the right hand side, again elongated tail at the right, more data in the right tail than would be expected in a normal distribution. Sometimes you see the distribution like this. And so the question, I don't know, one of you asked that what do we do there? If we see something like this, then should we just basically say, well, we cannot fit a linear regression model? So the answer is actually you could still fit a linear regression model, but you can do some processing, like you can take a transformation. Usually a log transformation, natural log transformation can make your distribution sort of more bell-shaped. Okay. So the natural log transformation is sort of a remedy for a lot of other situations. There is also another fundamental assumption we make in linear regression about the variance, and the natural logarithm transformation can also address like when there is a departure from the variance, constant variance assumption. So again, to keep in mind that there are ways of dealing with departure or violation of assumptions. Okay, so let's quickly do these measures of location. So the mean for continuous distributions, the mean is, again, as we all know, the average value, and it's given by sum of the observations divided by n, where n is the sample size. Median is the middle value of a distribution, and mode is the most frequently observed value. It's not suitable for small samples. The median is most affected by extreme values or outliers. The median is much more robust. So if you have skewed data, then you should report the median and not the mean, because the mean gets affected by, severely affected by extreme data points. Measures of spread. Range is the difference between the maximum and the minimum value. It's very sensitive to outliers, as you can imagine. What is interquartile range? We all know what median is. Median is the 50th percentile. And in the box plot, the two range of the boxes I was showing was the 25th and the 75th percentile. The interquartile range is the difference between the 25th and the 70th percentile. Okay, so that's the IQR. Again, it's a measure of spread. Mean, median, mode, these are all called measures of location or measures of central tendency, right? On an average, what is happening. And IQR, range, standard deviation are all measures of spread. How much spread there is around some measure of central tendency. So the most popular measure of spread is the variance, sample variance. So the sample variance, conceptually, you all know what variance is, and you all can calculate using your favorite software what mean and variance is. But conceptually, what does it mean? What is variance? Why do we? I mean, in plain English, if I said, tell me what variance is,
Like,
how far each value is
how far each value is away from the central point of the.
not only how far each value. So it's basically telling you, yes, the way you construct it is you take the difference of each value from the mean, you square it and sum it, right? So it's the average distance of each data point from a measure of center. In this case, it's the mean. But it tells you about how spread the data is. So if I have the variance of a data set to be, I'm just making it up, to be 50 versus the variance of another data set to be 100, let's say both have mean equal to, I'm making it up, both have mean equal to 25 or 50, let's say. So both have mean equal to 50, but for one, the variance is, I'll change the number. So for one, the variance is 25, and for the other, the variance is 40. So conceptually, or can you visualize the two distributions? Fine. Both are centered at the same point, right? Here, let's say. But if I were to draw a histogram for these two, so one would have kind of a tighter spike around that knee, and then another would have a much fatter distribution, spread out. So that's why it's called the measure of spread. Okay, so it can be have the same exact same mean, but the measure of spread tells us how much uncertainty, and in fact this we will carry on when we talk about estimation, how much uncertainty there is about that mean. The one with more variance has more uncertainty because it's more variable, whereas the one with smaller variance is more precise because it has a tighter distribution around that. Okay, the standard deviation is basically the square root of the variance. Now, some descriptions for categorical variables. Typically, we use frequency counts, frequency distribution. Say, let's say we are looking at behavioral pattern, type A1, A2, B3, B4 personality. And these are nominal, right? There is no inherent ordering. At least I don't know. I'm not a mental health expert, so I don't know if there is an inherent ordering. But I'm going to treat this as nominal, like hair color, eye color. And so what would you do? You would look at the frequency distribution. So for each category, you have the frequencies here in the first column. The total sample size was 3,154, and the percent frequency of the frequency in each category is 2. For A1, it's 264 over 3154. For A2 is 1325 over 3154, and so on. So looks like 42% of the sample are A2 behavioral type, 38.55% are B3, and so on. Okay, and then the cumulative frequency is, or the percent is, and thus, so I can say 50.38% are A1 or A2, because you're adding up the frequencies for A1 and A2. 88.93% are A1, A2, or A3, and so on. If the categories are ordered, then also you can give cumulative percentages. And here again is a histogram of the personality types. Yes.
It's like when we are measuring dispersion, like why do we have to see the deviation of each individual value from the mean, then square it, divide and have a root? Why can't we just see the differences, sum them, and then divide by the number of samples?
Why are you taking the square root? I'll sit for a second. That's conventional. The variance is without the square root. And the standard deviation is defined as the square root of the variance. One way to think about it is because taking the square root brings it back to the scale of the original measurement. Right?
No, I'm asking like you are squaring and then dividing and taking the square root.
Yeah.
Instead of that, if I take a modulus value of the difference, like
modulus value, not the square.
And then divide it by the number of samples.
Okay, great. Okay. Great question. Thank you. So if I take the absolute modulus value instead of squaring it, can anybody Does anybody have any insight why or why not? Before kind of getting answers, there is a metric which takes the absolute value. It's called mean absolute deviation. But let's come back to your question. Why would taking the square be more advantageous than the modulus value, absolute value? We remember the graphs. Why were we taking the square?
So negative
Positive and negative values, and more than that. Here also I would have taken the modulus, right? So the distance measure, Euclidean distance measure, is based on the square issue. So it's like it becomes like a distance. The squaring makes it more like a distance. There are other mathematical reasons, and all I'm going to say that you do have a metric like that. It's not that it's nobody has thought about that. So there is a metric that takes the absolute value, and instead of squaring and taking the average, you take the absolute values, add them up, and divide by sample size. So there is a metric like that. But analytically,
How close is this metric to the SD?
how close it is, it can be. That's actually a great question. I mean, I think there will be variation from sample to sample, but the bottom line is analytically taking the square and doing that way is much more tractable than working with absolute values. That's the reason. So that there's a mathematical reason why that is chosen over taking. But there are parallel measures that use the absolute value. And one easy way to sort of understand this is because the squaring makes it more like a distance, like a Euclidean. If you think about distance in the Euclidean space, then it's more like a distance. Like again, when you all of us kind of did like 10th grade algebra, right? Where we like if you take 2 points, how do you calculate the distance? You take the difference in the x coordinates, square it up plus difference in y coordinates. So it's based on that. So it's more like a distance. Okay. Now some two variable descriptions and some tests of association. Two variable descriptions. So now we are talking about like y versus x. Is there a relationship? Is there an association? That kind of question. Is behavior pattern associated with LPP? So there you need to consider the classification of variables. And as I said, in the regression setup, it is very important to understand what is the measurement scale of the outcome variable. Is it continuous? Because then it's linear regression. Is it binary? Then it's logistic regression. Is it count data? Then it's constant regression. And so that's very important. And also for the predictors, interestingly, remember the predictors are, we haven't formally talked about regression yet, but I'm kind of taking the liberty to do a little bit of digression and talk about it. So in the regression, so there is a y outcome that you are trying to predict, right? And that is usually on the left-hand side of the equation. On the right-hand side of the equation are all my predictors. Is BMI predictive of LDL? Is there a difference in LDL by gender, by age? Is dietary pattern predictive of LDL, and so on. So my predictors are on the right-hand side of the equation. Okay. So the good news is that why the outcome determines what kind of regression framework you are going to construct. the things on the right hand side, the predictors can be anything. They can be continuous, for example, BMI. They can be binary, for example, gender. They can be categorical, like if you have age groups, ordinal categorical. They can be nominal, for example, like race, ethnicity. So the things on the right hand side of the equation can be a mix of different kind of variables. And all the regression models are very flexible to entertain that whatever is on the right hand side can be a mix of different measurement scales. It's what is on the left hand side, the Y, that determines the particular type of regression. Is that clear? Okay, so again, I kind of said here, again, depending on the outcome, continuous or categorical, and the predictor can be anything. Then you would have regression. You could compare means within categories using t-tests, ANOVA. Whereas if the outcome is categorical, which is sort of what you want to hear about tomorrow, then what we have is we are analyzing frequencies, right? So then you have a table of frequencies, 2x2 tables, 2x-k tables. You have what are called chi-square tests of association. So so somebody was mentioning t-test versus chi-square. It's not, again, it's not about like when do we use this. It's more dictated by what the outcome type is. Okay, so that's the basic sort of basic framework. Continuous predictor, continuous outcome. You have a bivariate sample like this. We can construct sample mean, sample variances. Covariance is a quantity that basically tells how does y and x co-vary between each other. It is a function of the correlation coefficient, the Pearson correlation coefficient that you all are sort of familiar with. So the Pearson correlation coefficient measures the linear association between y and x, and it's a number between -1 and +1. Negative correlation means is a negative association, meaning as x increases, y decreases, and vice versa. And positive correlation means that it's a positive association, meaning as x increases, y increases, or as x decreases, y decreases. So that's the Pearson correlation. Again, these are all measures to understand the bivariate association between y and x. There's another kind of correlation which is called the Spearman rank correlation. And the simplest way to understand rank correlation is if you take LDL, if you take BMI, you can calculate the Pearson correlation coefficient. How would you get the Pearson rank correlation? You would rank the LDL values, you would rank the BMI values, and so now you converted the values to ranks, and you just calculate the Pearson correlation coefficient in the ranks. Okay, so that's the it still measures the linear association, but the linear association between the ranks of x and y.
Ranks will be classes.
Ranks will be like, let's say if you have a sample of size 50, then the ranks for each will go from 1 to 50. But the subject who is, I'm just making that, the subject who is ranked number 1 on LDL may be ranked number 5 in BMI. So you could have pairs like 1, 5, maybe 2, 10, 3, 2. So now you are constructing the correlation, Pearson correlation between the ranks. You have converted the original values to the ranks.
So that means for normally distribution, we can do stuff. That's Spearman, we have
Or for like categorical data, you can do. Yeah. So this is exactly like the what as it describes. So coming back to your question, so here like I conveniently chose two variables where x is 1, 2, 3, 4, 5, and y is some measure with values 2.1, 8.2, 5.3, 3.8, 1.1. So Pearson correlation between x and y is 0.36 here. Now, what about the ranks? Rank of x is basically x because it's already ranked like that 1, 2, 3, 4, 5. What is rank of y? If you order the y's, then the smallest one is 1.1, so that gets a rank of 1. The next one is 2.1, that gets a rank of 2. But 8.2 is the largest, so that gets a rank of 5. So now I have converted y to the rank of y. And now I calculate the Pearson correlation coefficient between rank of x and rank of y. That is my Spearman rank correlation, and it's 0.4. Here, this is a very toy example. That's why it sort of looks like this, but that's the philosophy. Okay. So for non-normal data, yes, you are right. For non-normal data, you would calculate the rank correlations. And there is also there's a whole branch of statistics called non-parametric statistics. So typically when your data does not follow a kind of a known distribution, does not follow normal distribution, you do non-parametric tests because it makes you free from assuming that that it's normal. So a few words here. What do I mean by it makes you free? So again, a little bit of statistical philosophy here. So we all know there is no free lunch, right? To get something, you have to pay something. So all the inference, the hypothesis test for regression, all of that stuff, your t-test, ANOVA, and broadly the statistical regression, the linear regression assumes normality. And the reason why it assumes normality is under normality, things are, it's a good situation, and large sample size. I mean, we have a lot of theorems. There's one very powerful theorem called the central limit theorem, which tells us that even if you have slight departure from normality, but as you increase your sample size, your mean starts looking like more and more bell-shaped. So the reason why we love to use additive normal distribution is it lets you buy a lot. Let's put it that way. But we also said that there's no free lunch. I mean, you have to first check. I mean, are you giving up a normal? And if it doesn't sort of satisfy a normal distribution, you are going to make you will be prone to making biased conclusions, biased inference, inaccurate inference. So, what non-parametric statistics is all about is that let's make us free of making any assumptions of how the distribution is. That frees you from having to adhere to that sort of a shape of your data or some other assumptions. And the reason non-parametric statistics has become more and more popular in complex data settings is because classical, we call these kind of inference that we are talking about classical inference, meaning that there is a lot of underlying assumptions. They are very powerful set of models, but again, there are lots of assumptions. So, in the case that those assumptions are not valid, what can we do? Non-parametric statistics is all about that, like small sample, like very weird skewed type of distributions, lots of outliers that maybe convey some important message about the design space, sparse data, certain categories. So there, non-parametric techniques work much better because you are kind of free from that normality, sort of restriction and all that stuff. So it's a branch of statistics that deal with those methods where now you in a way you get less in the sense, um, um, like if normality were truly to be valid, you get much more powerful inference. But the whole point is, if normality was not valid, what options do you have? I mean, do I throw up my hands in the air and I say, you know what, I don't have normal data, so let's stop, let's go to lunch and go party. We can't do anything. So that's one option, or the other option is, okay, let's try to make sense of what we have. And that's the whole spirit of these alternative modeling methods, that in the absence or in the face of inadequacy of the assumptions, what can be? Okay, so I kind of gave you a long answer, but yes.
How much will be the deviation? Like, suppose if I get into the habit of doing every data non-parametric, then how much will be the error?
Okay, so that's exactly what I was touching on. It's not how much of the deviation, it's about, as I said, the linear regression model or normal regression, we assume normally. But the good news is, because of powerful results like central limit theorem, these models are very robust. Even if you have a little bit of deviation from normal, you are still going to be okay and safe. These models are very powerful. So it's almost like a trade-off between, okay, how much deviation is it's like, okay, there is deviation, but you know what? It's not going to affect the results. That's sort of an understanding versus when we go to non-parametric, as you were. It's not a single answer that I can give you that, well, if the sample size is like less than 30, then do it. No, it is almost like you kind of develop with experience that when is it that your violation is going to be still okay versus when it is that you need to go to alternative procedures. Just as a rule of thumb, for example, you will see like tomorrow, like when we have sparse cells in categorical data, there's a test that's called Fisher's exact test that adjusts for that sparse cell. So in that situation, I can tell you a rule of thumb is, if the expected cell frequency is less than 5, then it's always better to close your eyes and just do this exact test. But in most of other situations, it's really kind of on a case by case, have to evaluate. Am I someone who would trash the classical regression method and say that, I don't want to deal with checking that assumption and go with totally like, distribution free statistics? I wouldn't, because this is a very powerful framework. And if I can, and because it is robust to this kind of normality departure, I am going to rely on it heavily unless there is very extreme sort of evidence. So that comes with experience, and that I cannot tell you that there is a single answer to that.
I have one very basic question. Madam, like we are doing this correlation between this X and Y. Suppose in Pearson correlation in your data you are showing it's 0.36, and in the same when we are putting in rank we are getting 0.5. What is the difference? When I am, suppose I'm not a statistician, not doing any research, and I'm reading something and getting two data, what I will interpret?
Like, so what is the relation? Two different ranks.
No, that's correlation value.
Yeah.
Suppose I'm getting 0.36, then somewhere I'm getting 1.
Oh, yeah. 0.36 versus 1 is a huge difference.
Yeah, difference is huge. But how I will correlate, interpret this?
Yeah,
Whether this
one
is
0.36, I mean, roughly speaking, like if I were to sort of, so we are only talking about this part, right? So if I were to this X and this Y, although this is kind of toy data, if I were to run a regression model of y versus x here, the R square from this model, meaning like what is the quality of the prediction, would be roughly about 0.36 square. Okay. So about, and I'm just mentally doing the math, it's about 12%. Which is saying in interpretation only 12% of the variation in y, let's say L, is being explained by BMI. Whereas if the correlation is 1, I'm saying 100%, which is not going to happen. 100% of the variation in LDL is being explained by BMI.
One question is aspect, like apart from like BMI, is like add more variables.
Yeah, okay.
So in that situation, will that predicted percentage change?
Of course, it will change, but there, the interpretation of the R square, because there are multiple x values, so then it is not about square of the Pearson correlation. Here I could do this mentally because there is only one variable.
But why I'm asking is because when we are in one variable as the
Primary exposure.
the one that is predicting the outcome.
Yeah.
So then I am getting 1 R square, that is 12%.
Yeah.
But is it like God's truth that the variation is that part is 12% only indicated by that? Or if I add more variables, that percentage which is depending on that will change.
Can change. Yeah. Because okay. Again, great question. So I first interpreted your question differently. I thought whether the R square is. The R square will of course change. Because as you add more variables, the R square will increase. Because you are explaining more and more variation. Suppose with BMI you add age, you add gender, da 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 da. So the R square from 12% will, let's say, will go to, as you keep on increasing variables, it will increase. Let's say it goes to, I'm making it up, 36% or 45%. So then I'll say 45% of the variation in LDL is explained by BMI, age, gender, smoking, whatever. Okay, so that is one part of the question. But the way you explained it later, that's a more interesting question. If we're saying that okay, I got 12% when I ran the model with only BMI. So I said BMI alone explains 12% of the variation in LDL. Now I add age, gender, smoking. I know that overall the R square went to 45%, but could it be that now BMI in the presence of age, gender, smoking can explain more? And I am saying it can, because the impact of BMI on LDL could be synergistic with the other things I added, or it could be antagonistic. If it's antagonistic, actually it will slip down. Right? If it's on the other hand, if the impact of BMI is enhanced, and there are many clinical variables like that, where adding another variable might enhance the impact of BMI on health. You guys will be able to give me better examples. I don't have examples on the top of my head, but it can happen. That it enhances the impact of BMI on health. And there is.
Like if we add smoking.
If you add smoking, yeah. So that could happen.
Then how to calculate about that?
Oh, yes. You can calculate. So there are tricks you can do. Like you can fit the model with and without, BMI. Yeah, and then compare. That's it. Does that make sense? So again, conceptually, thank you for again that asking that question and like how to do that. I did not tell you how you can build the software, but I told you fundamentally how to think about doing that, and immediately got it, right? Because you basically what you do is you pick a model with BMI and all those variables, and without BMI part with those variables. And you just compare the R square between those two models, which will tell you like did BMI really enhance or not.
Another very basic question.
No
We
question.
have, we have two variables, X and Y. If one is parametric and the other is non-parametric, then what
Variables cannot be parametric or non-parametric.
the distribution of it?
Well, again, the distribution of so okay. Again, let me try to explain. Again, this is a really again great question because it delves into the philosophy. So, a variable cannot be parametric or non-parametric because a variable in a certain paradigm you will assume as a distribution or not. If you assume that you are going to work in a paradigm where your variables have distribution, then it's a parametric model. Whereas when you are into the non-parametric, you are basically exactly you are basically in the paradigm where everything is distribution free. So it's the kind of the paradigm or the framework you are in. Does it make sense? So you can use the paradigm can be that one variable is normal, another variable is binomial, another variable is conform. You can have that. Like, your X predictors can be right. But in the parametric framework, every variable will have conceptually a distribution.
We'll break for lunch in
Yes.
half an hour.
Okay, sounds good. So this is Pearson correlation again. One other point that I wanted to make. This is a slide where this is a slide where to make the point that a picture is worth 1,000 words. Okay, so this is a y versus x. Again, a toy example. I have connected the points, and here is the shape of the curves or the association between y and x. If you calculate the Pearson correlation, then it is 0.91. If you take the same data, calculate the ranks of the y-x, compute a Spearman correlation, the Spearman correlation is 1. So for both the Pearson and the Spearman correlation, basically I'm saying that there is a strong association, like a near one, meaning like near part there. But is this linear? This is far from linear. So the whole point about this slide is if you blindly just computed those statistics, the Spearman correlation, the Pearson correlation, and you said, well, there's like a perfect correlation, and you fitted a linear regression model to estimate the best fit line, and you would get the best fit line. I wish I could draw it. Well, I'll try to draw it here. You would get yeah. Yeah. So let's say I don't have one. I'm just doing the shape of the graph, right? And let's say your scattered square level. If you only calculated the correlation coefficients and you fitted a linear regression model, so the best fit line using the theory of least square would kind of get you a line like this, right? But we all know, looking at the simple sort of plots, that it could be a very wrong representation of the data. So here is an example of where like a picture is worth 1,000 words. If you only look at this scatter plot, this picture, you would know that a linear model will not hold here. You have to do something. What is that something? Anybody has idea where I could still maybe tweak my linear model to estimate this curve?
Take a log,
Take a log transformation. Any other ideas? You were saying something. I think. Log.
the curve looks exponentials.
Okay. Okay. So take a log. Would be one approach. Take a log of which one? The y, the x, or both? Of the y. Okay. Anything else that jumps out at you? So remember the linear regression or the linear model helps you fit the best straight line to a scatter of points that looks like a straight line. Looks like a straight line, right? It doesn't have to be perfectly on a straight line. So is there something that, okay, logarithms, but something that is even more basic that might work here?
Polynomial,
Polynomial.
the negative value.
Polynomial, okay, polynomial is another way. Polynomial is basically adding terms. Like for example, instead of only having x, this looks like a cubic, right? So you can add x squared, x cubed. That's what you were saying, right? So you can fit a polynomial, and that also you can do within the context of a linear model. Okay. So logarithm, polynomial. These are so all of these. Do you see why I made that point that even if it looks like kind of is not a straight line, but you can do tweaks within your linear regression model to entertain linear regression in modeling something like this. So logarithm is one, polynomial is another. I'm saying there's a third option. Look at the picture. Think out of the box completely. Forget about like logarithm, polynomial. Just look at the plot. How about this? I'm going to go back to the in Pondicherry you probably know not Pondicherry in Chandigarh, PTI. So they took us to a restaurant called Back to Source. Yeah, so it's a corner, then I lost the name also. So here is I'm going to go to back to source.
Okay.
So back to basics. How about this? I'm going to say, this piece I can fit a space. Oh my god. I am sorry, I got excited. Take care of it. It's too smart words, I guess. Yeah. Okay, so I'm going to go back to okay. So I'm saying, you know what? I'm going to I didn't draw the scatter plot nicely. There's point here. Yes. Yes. Again, I do this and then like a straight line here. This part is another straight line, and this part is another straight line. Exactly. So until see, I have actually mixed up 6 steps, 3 pieces. And do you see with 3 segments, straight lines, I can actually mimic that cubic So this is called piecewise linear. Because each piece is a straight line. And I can fit this in the linear model.
There is another model of moving average.
Yes, but that's a very different concept. That comes from time series data. That comes from time series. This is different. This is a class of models, falls in the class of models called splines. Have you heard of splines? So splines are basically pieces, little pieces, joined at these are called knots. That's why I was saying, go back to the basic. Like, just look at the picture. Seems like there are 3 segments. If I could model each segment with a straight line, I could actually make this curve. So this is called a piecewise linear model, and you can see this linear region. Okay, and then finally, this was again more about how do you test for significance of correlations, but this is lesser of an issue. When are we have to break? Another? Okay. So let's look at this. So now we talked about sort of distributions of variables. We talked about graphical representation. We talked about different kinds of like parametric versus non-parametric approaches. We talked about, in fact, we talked about a lot because I digressed, but I think it's okay. Let's talk about now how to make inference about the probability distribution of a variable. Is the fair coin? Is the coin fair? What is the average rate of teenagers in Michigan? Is the coin fair, or is there disease? Does this person have disease? It's like you're trying to estimate a probability, right? Probability of cancer, risk of cancer. Questions like what is the average rate of teenagers in Michigan? It's like we're trying to make inference about the mean of a distribution. And then third question, what is the relationship between height and weight? This is like you're trying to make inference about the slope of a regression. Slope of BMI LDL, slope of height with weight. So beta is a regression coefficient. So in all of these, there is a population slope and we have a sample at hand. Based on the sample, we are trying to make an inference about the population slope or the population mean or the population proportion. So the proportion or the mean or the slope, these are all called what in the population are quantities that are unknown. These are called parameters. Parameters statistically. So it is a collection in a population, it's a collection of units in whom we are interested. Let's say all people living in the United States in the study of treatment for diabetes, all people with diabetes. So these are, and this is basically population, and each of those attributes you can think as parameter. As I said, statistical inference is all about inferring about the population based on a sample, because we don't have infinite resources to census everyone, right? In the population, it is impossible to measure each and every unit. So a practical approach is you sample and usually you draw random small subset of units from the population, and the sample is measured and studied to draw conclusions about the population. So the way you draw the sample, that is a key step in any statistical investigation, because in order to make your inference generalizable to the population, you have to make sure that you are drawing a sample that is representative of the population. Okay. So although I just mentioned it in one bullet point, this is a very, very important point in statistical design. Because oftentimes we come across studies where no clever analytic method can remedy if the sample was biased in the first place. If there was selection bias, like you do from a subgroup of people who, say for example, you are looking at um, you are looking at um, um, income and education. Okay, so the relationship income and education, and you go and actually sample instead of sampling from the entire population, you go and sample from a group of like sort of a doctors, or you sample a group from a group of university professors. It's a very selection bias type of scenario because of course these people are going to be at the very high end of the education strata. So you are not going to be getting a very representative sample of the population. And what your inference would be biased because you have selected like a very biased sample. So always you have to make sure that your sample is representative of the entire population that you are trying to make inference about. Inference for a population is based on a sample. So the statistical inference is the process of making inferences about parameters of a population based on sample data. Let's say we are looking at weight of teenagers in Michigan, and if we could conduct census of all teenagers in Michigan, we would get true mean. This Greek letter mu is the true mean in the population. So this is a parameter. And true standard deviation, again the Greek letter sigma, denotes the true standard deviation in the population. So both mu and sigma are what I call my parameters because they are unknown, but they are the true mean and standard deviation of the population. We don't know that. So what do? We want to estimate this. So we choose a random sample of teenagers. We randomly select, say, middle and high schoolers. And we, based on our sample, we get the sample mean. I denote it by X with a bar on the top. And the sample standard deviation, which I write it as little s. So here is my population. And the mean and the standard deviation of the population are true but unknown. These are my parameters. And here is my sample that I draw randomly from the population. The sample mean and the sample standard deviation are X bar and S. And I am going to use X bar and S to make some conclusions or to give some estimates, guesses about the population mean and the population standard deviation. So all good. Now the question is, what do X bar and S tell us about mu and sigma? Because remember, mu and sigma, I don't know. What would I ideally want? I would want that my X bar and S to be as close to the population values, because then I would make less error. Okay? Everybody with me? So this is a very fundamental concept, and we are broaching into the territory of what we call sampling variability, which is a very hard concept kind of to get, but if you get it and it stays with you. And I want you to sort of have that. So now when I say I want it to be as close to the population mean and the population standard deviation, how do I know how close, how much sampling vary? So this is a very, very important slide, and I'm sorry, I thought I had this in color, red color, but Okay, so let's try this. So here, this box, this is my population, this rectangular box. Okay. And there are about 20 people in this room. So what I tell you is, each of you go and draw a random sample of, I think there are 8 in each table box, 1, 2, 3, 4, 5, 6, 7, 8. So each of you go and from the same population, so go to Patwabon and South Point, close by, to school. Each of you go and draw a random sample of 8 middle and high schoolers from those 2 schools. Okay, so you come back with your sample, you come back with your sample, and each of you come back with your sample. I tell you that based on your sample at hand, calculate the mean and the standard deviation based on your sample. So now tell me, so each of you got a random sample of size 8 from the same population. Will your mean be the same as yours? Will your standard deviation be the same as yours? No. Right? Each of you will get a different mean. Some of you may get the same mean, but each of you will get a different mean and different standard deviation. So then, if there are 20 people in this class, I will get 20 sets of sample means and sample standard deviation. Okay. So now I tell you, so let's take those 20 sets of sample mean and sample standard deviation, and let's draw a histogram of the sample means. This is the one. So this says sample size 10, but for now ignore it. Okay, so it's 8. So I draw a histogram. So the histogram now is based on 20 means, each calculated based on 8, a sample size of 8. And as you can see that there is a spread around those 20 means. But the point is that the distribution, if you each picked a random sample, if your sample was not biased, that's a big kind of requirement. If none of you, I mean, for lack of a better word, if none of you were lazy, none of you cheated, and you all got like random samples, then the histogram will be centered around the population mean. Okay, but there is even more striking about this, or stronger. It turns out that so there's a histogram, there's a spread. The red line around that Greek letter mu is basically saying that's the population mean, and your sample means 20 should be spread around that mu, and let's say that is the histogram shows the spread. Now the sort of the beauty of central limit theorem. So central limit theorem, there's a theorem at the back that says if I now send you back again to the same population of these schools and say and told you, each of you, instead of drawing a random sample of 8, get me a random sample of 50. So each of you get a random sample of 50. And again come back, calculate your mean and standard deviation based on each of those samples. So again, I have 20 sets of means and standard deviations. But now I tell you, draw a histogram of those 20 means that are based on a sample of size 50. Can you guess what will happen?
Resolution.
Exactly. The spread will become tighter. And the more and more you increase your sample size, the more and more like that mu will still stay the same because it's the same unknown population, but your spread around that red line will start to shrink more and more. So why do I say it's a powerful result? Because conceptually, what are you saying? That when if I did not change, if I got hurt, if I went and do a random sample, and if I can have a moderate to large sample size, then not only am I going to make a more and more accurate guess about my unknown mean, but actually I will also have more precision in my estimate. I will be more and more sure that it is indeed that red line. Because if it is like this, and the further it is, well, it is here, but look, there is a lot of distribution also on this side, on that side. So I am less sure that it is the red line. Whereas if it is like this, I am very sure that it is that red line. So I am, it's like, like a dart, like there's a, what is it called? Dart. I don't know. Do we play dart here? Yeah. So you're throwing kind of your guesses, and you want to hit the bullseye. So you're going here, there, here. So like what this is saying that if you are making like 3 guesses versus 100 guesses, of course you are going to get more and more centered and precise, closer to what the truth is. So that's what is happening. So you are going to get a more accurate, more precise estimate. And that is the fundamental basis of statistical inference. And actually, that is the fundamental idea behind confidence interval. You all have learned confidence interval or have encountered. So, what is the interpretation of confidence interval? So, exactly, and can actually let's do it. How do you understand confidence? What is about 95% confidence?
So just try to like
Your estimate of the mean will either be in the intervals or will not be in the interval. But the confidence interval, even let's say I'm 95% confident, but the confidence interval also has a repeated sampling perspective. What it says again, let's say if you did it 100 times, 95 of the time actually your interval will capture the mean. But you might be like, again, let's see, there are 100 people here. You might be the sort of the 5 within the 5% that meets it. But not, so your interval will either capture it or not capture it. There's not a 95% probability, right? It will be either a 0 or a 1, hit or miss. But what it's saying is that if there were 100 people in the room, for 95 of them, that interval will contain the true mean. 5 of them will miss it. You might be one of the 5. You might be one of the 5. But the rest, like you like will be among the 95 that got it. And so that's what confidence interval is.
still not clear. Like what's the difference?
What's the difference? So you say, okay, you gave me a confidence. Let's understand 10 to 25. So you told me that there's a 95% chance that the true mean is between 10 and 25. I'm saying that's not exactly right. Chance-wise, between the 10 to 25, and let's say for the sake of reasoning, the true mean is, I'm just saying, in your case, You said 10 to 25. So let's say the true mean is 9. So the 10 to 25 interval that you gave does not capture it. 9 is outside. So there is not a 95% chance. It's either there or it's not there. But what the repeated sampling is saying is that if again I told each of you to go and get your sample, calculate the confidence interval, then for 95 of those intervals, so you might get a confidence interval of 8 to 23. So yours will capture 9. You might get an interval of, I'm again making it up, 7 to 21. Yours will capture it. So 95% of the intervals will capture it. And there are 5 that will miss it. So it gives you that. So the attaching the 95% confidence statement is correct because you're saying I'm 95% confident that the population mean lies there. So another analogy that I like to give when I'm talking about confidence interval 3 of any math is basically, let's say there's a butterfly in the room. That sort of, although that has to be a static butterfly, it cannot fly around. That's sitting in one corner of the room and it's a dark room. And you have a butterfly net and you are trying to catch it. So you shoot once, another time, another time. So either, it could be a flying butterfly. So either you catch it or you miss it. Right? So the butterfly net is like the confidence interval. Like, think about it as if like 95 of the times, if it 100 times, you would catch it, and 5 times you miss it. But every time, either you catch it or you miss it. So the confidence interval or interpretation always has that repeated sampling interpretation, just like in the previous slide before, when we talked about, like I sent each of you, you get your sample, you get your mean, and then draw the sampling distribution. This is a very fundamental concept in statistics, and initially, for the first time when you encounter it, it's hard. I myself, when I encountered it, it's hard, and I'll tell you exactly what goes on in your mind. You are thinking, well, I have a sample, I have the field, I have the force. What is he talking about variability? Right? You are using a single number. So when I say what is the variability, you are like, it's a single number. Where is she getting the variation from? The variation concept is coming from the repeated samples. So the mean also has a distribution. That's hard to conceptually get when you first encounter it, because you think, well, it's a single number. Why am I talking about a distribution? That's the sampling variable. So basically, again, just wrapping up and the same fundamental points we already said. What happens to a normalized histogram when the sample size increases? It becomes more and more like my bell shape, and that is due to the central limit theorem.
From this sampling variable, I got the various means, the various samples, that will always be always true.
No, it might start looking from, like, if the sample size is small, let's say 5, it might start looking very skewed because there's a lot of flux. We all know, like a sample of size 5 versus a sample of size 50. There's much less sort of variability in size 50 than a size 5, because on a sample of size 5, if you slightly change 2 numbers, it kind of goes over the mean a lot. Whereas when you have a sample of size 50, a slight change in 2 numbers doesn't happen. So you are taking kind of the average.
So as my sample is like more and more representative of the population every time, then the distribution of the mean will be more and more symmetrical, well shaped.
the actual central that part that even if you started from a non-normal distribution, but you kept on taking means with more and more sample size, the distribution of the means will start looking normal. So that's why like you all might think, oh, statisticians are really greedy people. They just want more sample size. The reason we want more sample size is because then central limit theorem tells us that it starts behaving more and more like a normal distribution. And as it starts behaving more and more like a normal distribution, we can use all these like sort of classical inference and all these properties. So that's the it and more and more normal distribution and less variable, right? Less and less variable meaning more and more precise. Right? That makes sense. Okay. So I think we'll stop here. So here is the normal distribution again, just some characteristics. This is how it looks. There is a probability density function that sort of looks, there's a mathematical expression behind the shape of this curve. This is a very standard distribution function. It's characterized by two things, the mean and the standard deviation, the mu and sigma as I wrote. And here are sort of deviations from normal in terms of the skewness. Okay. So let's stop here, take a break, and then we will sort of
December 45.
say it again.
December 45.
Now we break for lunch. So morning we have had a statistical piece. So now it's time to have a piece. So we will reassemble here at around 2:50, 2:50.
Okay.
50 or 50? Advance should be sufficient.
It's okay for you want to work. Yes, do it process.
To pay for the. So,
I will need to go to the restroom.
আমাদের জন্য separately করা করবো understand so much in type of orientation and variation. So did I put him in software preferably software.
এই টেস্ট করে এই করতে এই করতে গেছে এই জায়গাটা আমাদের দরকার এই জায়গাটা পেতে দিয়ে তারপর
একটা ওইগুলো খুব ভালো বলছিল যে এই ভ্যারিয়েবল ভালো না মানে আমাদের কাছে ওটা ভালো বলছো আমাদের কাছে বলবো যে এই ভ্যারিয়েবল হলে তুমি এই জিনিসটা করবে এগুলো এইভাবে এইটা হলে এই ইন্টারপ্রিটেশন করবে
বা এই লেখাটা মানে সফটওয়্যার দিয়ে দেখা যাচ্ছে রেফারেন্সটা কেন আমরা আমি যেমন আমাদের দেখি না
সেটা এগুলো চলে যাচ্ছে
যেমন আমরা কি আমরা ডেটা তারপরে এসেছে কিভাবে ডেটা একটা অ্যানালিসিস
আমি খেয়ে নিই তারপরে।
মানে হয়েছে
না,
আমি দেখি। আরে আমি জানি চলে গেছে তো এই ব্যাপারে বিষয়টা কখনো ছিল তুমি বলো স্যার হুম না না আমি বলেছি যদি চলা পুরো ওরা ভাবতে পারে তবেই ভাবছে বললে হবে না দেখো ও আমি যে বলছি ঈদ আছে পয়সা দিচ্ছে আমরা তো তার করোনা আমি ছাড়তে পারবে না আমার জবে হবে আপনি আপনি বললেন আজকে আপনি দেখুন আমি ওরকম খাচ্ছি কিন্তু ম্যাডাম বলেছে যতক্ষণ না সিস্টার বলবি আপনি একদম ক্লিয়ারলি বলবেন ম্যাডাম বলেছেন আমি সিস্টাররা বললি ওরাই না খাতে পারছি ততক্ষণ আমরা আপনি সেটা আপনি নো আমাকে খুব বলছে আমার এই আছে ঈদ আছে বললে আমাকে যেরকম পাচ্ছে ইমপ্রুভ করবে সেটা তো ও উডল্যান্ডসে বলে ঘটা বেশি হয়ে যাচ্ছে মানে ঘটা বেশি হলে তো সেটা না আপনি অন্য জায়গায় সেটা করতে ও আমাকে বলছে টাকা অনেক আমি বলেছিলাম একটু পরে ফোন করে আমি লিখেছিলাম ঢোকাবে ওখানে কি হবে আমাকে আমাদের আইসিইউতে আছে প্রবাসন দেখি না ও বাংলাদেশে আছে ওখানে ভালো সবচেয়ে বেশি আমাদের যদি কেউ তাহলে আমি তোকে একদম ধুমধাম করে কিছু দেখা চাই তুই যে আমাকে ভাসিয়েছিস অমনি করে কেউ যায় এক মাসের নোটিস দিতে হয় না করে দাঁড়া এইটা ডক্টর বন্ধ করবে বলেছে তোর ইয়ে তোর এক্সপিরিয়েন্স আছে ডক্টর আজকেই বলে গেছে ওই জন্য আজকে এক্সপিরিয়েন্স থেকে না আমি তোকে ধুমধাম করে কিভাবে কোর্সটা সাইড করছি তো ইউ হ্যাভ টু আন্ডারস্ট্যান্ড একটা আমাকে 14 তারিখে এই সেমিনার থেকে
সবাই
কি হয়েছে
স্টপ করতে হবে একটা সবাই বাইরে আছে না সাউন্ডটা তো বন্ধ করতে হবে
Please unmute, ma'am.
আবার কিন্তু ফ্রিজ করে গেল।
হ্যাঁ, এবার করার পর
কোনটা দিয়ে?
এখানে ডাবল
ও এই ড্রয়ারগুলো দিয়ে কেন হচ্ছে না?
এটাতে আসছে না, স্ক্রিনে একবার একটু ক্লিক করে তখন এটাতে আসবে।
কিন্তু আচ্ছা, একবার ক্লিক করে নিলে তারপর আসছে।
এটাতে ক্লিক করছি, তখন মাউস পয়েন্টারটা এখানে চেঞ্জ করছে, এখানে আসছে। এটা আলাদা স্ক্রিন, এটা আলাদা। এখানে ইংলিশ আমরা ক্লিক করব।
আচ্ছা, ওকে, ঠিক আছে। ওকে, আর এভরিবডি ব্যাক? শুরু করব? So again, when we left the paradigm that we were talking about, the inference paradigm, taking from sample to population, and we saw that we can do this, but how accurately, that will depend on this various factors. Sample size that is one, sampling variability is another one. But the whole point is that you are taking the unknown parameter, like there's an unknown parameter in the population, and you are using your sample data to estimate through a statistic the unknown parameter. And very simply put, let's say you are trying to estimate the mean height, as we were saying, of children, of teenage children in India, in Kolkata, and your what are you basing it on? You go and draw random samples of teenage children, and you calculate your sample mean. So your sample mean is your estimate of the unknown population mean. So S to P, sample to population, and that's the idea. Okay, so this is what we were talking about. We talked about sample variability. আমরা দেখলাম যে I send everybody and they get a simple random sample of size n. They calculate their X bars, their sample means, and then if I plot a histogram, as you all said, that basically what happens is as the sample size increases, the histograms of the means which capture the sampling variability start looking more and more like the bell-shaped curve, normal distribution. So, how is there's a kind of a quantity that defines, and this comes from mathematical formula that defines this sampling variability in the mean. When I talk about sampling variability in the mean, I'm saying because the mean or sample mean also has a distribution, so there is a standard deviation of that distribution of the sample mean. That is called the standard error. এই ব্যাপারটাই I'm switching to Bengali for a second, for 30 seconds. এই fundamental ব্যাপারটা is very important to understand because we often get, how many people get confused with standard deviation versus standard error? Yes, and it's a very natural confusion. So, what is standard deviation? Let's talk about that and then we talk about standard error. So, you have went and you have gone and collected heights of 50 based on your random sample of size 50 heights of teenage children from the schools of Calcutta. You come back and you calculate a standard deviation based on your sample. So you calculate a mean and a standard deviation. That's the standard deviation of heights of teenage children based on your sample. What is standard error? Which is mean term. You calculate it based on your sample, and I said if I send all 20 of you and each of you collect 50, sample of size 50, you draw the histogram that has a distribution. So that is called the sampling distribution of the mean, of the sample mean. ওই যে histogram বা ওই যে histogramটা approach করছে a bell shaped curve, তারও তো একটা dispersion আছে, right? That also has a standard deviation. So the standard deviation of that sampling distribution of the mean is what I call standard error. Why is that important? Because that guy, that standard error is precisely telling which একটা plot দেখাচ্ছিলাম না যে অনেক variability, then another plot as you increase the sample size it becomes quick, like very center. So that has more precision. So the reason why the standard error is important is because the standard error tells me how much variability in the mean I had. And the more variability I have, that means I have less precision in the estimate. Right? So that fatter histogram has more variability in the mean, whereas the one that is very spiked and centered around the mean will give me a more precise estimate of the mean. Right? So standard error tells me exactly that. If you forgot everything else and only wanted to remember one thing to take home, the way to interpret a standard error is it gives you the precision of the estimate. So that's why it's such a key quantity. Whenever we talk about standard error of a regression coefficient, we are basically saying how variable is that coefficient, or in other words, how precise can I be in my like what is the level of precision for my estimate. So that's the basic difference between standard deviation and standard error. Whenever we talk about standard error, we are saying it is about the dispersion or the variation in a certain estimate. The larger it is, the more variable it is, so the less confidence I have about its accuracy. The smaller it is, the more precise it is, so I will have more confidence in its accuracy.
And what are the values are like? The values are
The values are, yeah, so the values, the mathematical formula that says what the standard error is given by like what is the population variance, standard deviation, that's sigma, and you in the denominator you have something like square root of n. That's why the sample size is important. When sample size goes up, that goes down, right? The variation goes down means you have more and more precise estimate. That's why the sample size is important. Now you might say, "We sigma ta kotha theke pabo?" Sigma ta to you just told me it's unknown. I don't know it. It's a population parameter. ওই sigma টাকে আমি estimate করব sample standard deviation দিয়ে। কিন্তু the standard error is not the sample standard deviation. The standard error is that divided by square root of n. কারণ আমি যত মিনটা যত মানে ক্যালকুলেট করার জন্য স্যাম্পল সাইজটা যত বাড়াচ্ছি তার মানে আমার বেসিক্যালি ওই মানে ভেরিয়েশন ইন দ্য মিন কমছে and I'm getting more and more precise estimate of the mean. So, more and more precise estimate of the mean, meaning the histogram becomes kind of more closer to that red line. ওই যে ছবিটা আগে দেখিয়েছিলাম। Make sense? Questions? If there is one thing that I want you to take back home and forget everything is, and this is like an important but difficult concept, is that we statisticians, like anything that we estimate, we always have to tell you about the level of uncertainty in that estimate, because for us it's not a deterministic world. It's not like centigrade Fahrenheit temperatures. It is because we have random error. So আমি বলতে পারি আমার, and oh yeah, that's another thing that reminds me. So why is it that when you are publishing in journal articles, why is it that statisticians will tell you when you are sort of presenting inferential results, if you just told me that the mean height is such and such, and will you stop there? Will you be ever able to publish your findings? No, because people will come and say, okay, I got what you did, and that's for the point estimate, the single number. But I don't know what's the level of uncertainty. So that's why you need to either give a confidence interval or you need to report the standard error. Typically in the journal articles, like in tables, people will report the point estimate. You see this all the time. Whether it's a linear regression or a logistic regression is key what? People would present the odds ratio. That's a different framework. We'll talk about it a little bit tomorrow. Odds ratio, but they give also 95% confidence interval about the odds ratio. Why? Because the odds ratio is just a single number, a point estimate. But in order for me to tell you how confident I am, how reliable that estimate is, I have to give you a level of uncertainty. And another way to interpret confidence interval is it actually tells you about the level of uncertainty in the estimate. If it's a very wide confidence interval, then it's like
Mean is usually given by mean plus minus standard deviation.
standard deviation নয় ওটা। ওটা
ST
mean
তো-
plus minus না,
আমাদের
যেটা mean plus minus ST যেটা দেওয়া হয় এটা হচ্ছে আপনার প্রথম টেবিল 1 ডেসক্রিপটিভ ক্যারেক্টারিস্টিক্স, সেখানে mean plus minus standard deviation হচ্ছে, কারণ you are just describing the sample.
মানে
কিন্তু যখন-
age, weight,
হ্যাঁ, that is your table 1 of any paper. Socio-demographic characteristics ইত্যাদি দেওয়া হচ্ছে। এবার কোন রকম মডেলিং করে এস্টিমেট বার করে দেওয়া হচ্ছে, তখন you are presenting standard error, not standard
estimate পাবো।
estimate যখন বার করা হচ্ছে। ওইটা যেটা mean plus minus standard deviation, that is like your descriptive table, usually your table 1 in any paper.
So now standard error and confidence interval, they're not the same.
They are not the same quantity, but same thing, but confidence interval has standard error packed into it. কারণ standard error is more like the the standard deviation of the estimate, right? But how do you get confidence? You get confidence interval by taking the point estimate plus minus the standard error times একটা critical value from a normal distribution or a key distribution, whatever the vector. So although they are not the same exact equivalent things, but they are functionally related. You can say that so there are 3 ways you can present results in a table for a journal article based on inferential statistics. What? One is you can present the estimate, point estimate, and the standard error. 2 numbers, 2 columns. Another is you can present the point estimate and the 95% confidence. And another way that you see journals report are present the point estimate, let's say the odds ratio, and then a p-value. Is it statistically significantly different from what the hypothesized value? So typically these are the three ways you can report your results. So there has been a lot of debate, discussion written about the medical community is hung up on p-values. I mean, I can do anything to get a significant p-value, right? That has been like, how do I get a significant p-value? So the medical community has been, and there has been a lot written in the statistical literature that we have to get people away from thinking that p-value is the end-all solution. And nowadays, what you will see, most of the top journals in clinical research, and Dr. Singh, I would like to hear your perspective on this. They are shifting away from that p-value mindset, and more editors are saying report confidence interval, because that not only gives you the sort of the point estimate, gives you the level of uncertainty, and people want to see that. Instead of being like a binary reject, do not reject based on p-value. So there's the American Statistical Association. There was lots written that how as a community, as a discipline, we can steer people away from the p-value mentality, because the p-value was becoming like a plague. Everybody was running to get kind of significant p-values. So that is a very positive thing that has happened, and I'm sure you have seen that, right? Most journals now are like, only reporting p-value is not enough. You have to give some level of sort of uncertainty, and the best way to do that, and there are again mathematical reasons why confidence interval, and like whether you reject or do not reject an null hypothesis based on hypothesis test, you can sort of figure it out from a confidence interval also. The confidence interval packs more information, and so there has been a major shift in the clinical literature to sort of advocate confidence.
As you said, that suppose there are n number of samples I can take from a target population, I can calculate from each of these. Now, suppose I have selected one particular sample and I have calculated the mean, and as you said, if I have to calculate the standard error of mean, I should know what is the population mean. But I don't know that, but we estimate.
We estimate that through the sample standard deviation, the one that Dr. Sinha was talking about. But then the standard error of the mean is that number divided by square root of n. And again, if you tell me where did you, again, this is sort of like, where did you get this square root of n, and like I don't understand. I have to tell you, I cannot show you because I need to do some math on that.
Regarding confidence interval, I have a question regarding. No.
Yeah, go ahead.
ওর প্রশ্নটা একটা আমারও প্রশ্ন ছিল যে we do an observation study, আমরা একটা স্যাম্পল নিচ্ছি, তার উপরে যদি আমরা এইটা আছে, তো how do we finding out the confidence interval from this one single sample that we are studying?
Yeah, and that's where the math.
That's where the math.
Yeah, and again, the point that you made, I will just take that opportunity. ওই কারণে আমি এক্স্যাক্টলি বলছিলাম যে স্যাম্পলিং ভেরিয়েবলের কনসেপ্টটা মানে সিঙ্ক করাটা না খুব ডিফিকাল্ট প্রথমে, যখন কারণ অ্যাজ ইউ জাস্ট সেড, আমার তো একটাই স্যাম্পল, আমার তো একটাই এক্সবার, আমার তো একটাই স্ট্যান্ডার্ড ডেভিয়েশন এস্টিমেট, তাহলে how do I know what the variability of that means? So lot of people struggle with that concept of sampling variable, because they're like, what are you talking about? I have only one number. What is variability of it? But that comes from the fundamentals of thinking about repeated sampling. If you could repeat sampling, if I could send each of you You will have separate samples, you will have separate X bars, so that's the very sampling variability you're talking.
Makes sense. So like, suppose I have samples on which I have done some study. And for each of the samples, I have found some information, whatever I wanted to collect. And I get the confidence interval also for the same. Like, suppose in one of my samples, my confidence interval is from 8 to 8.
Okay,
And another sample, my confidence interval is from 7 to 12.
okay,
So that indicates that in my second sample, where my confidence interval from 7 to 12 is there, it is more representative and more precise. It is more precise. Precise.
Yeah.
But like in the first sample, what indicated that value could range between 8 to 80, does it mean that truly it can range up to 80?
no, based on that sample again, because you have less precision. Let me just show that slide again. Where did that go? The
Point for understanding this question is that the 95% confidence interval which was given as 8 to 80,
Huh.
Whereas the others, the sample gave 7 to 12. Is the first confidence interval wrong?
no,
No. But-
it's not wrong.
But it is supposed to mean that if I do my test again and again with multiple samples, then my value should range between this to this. So one sample is
What the
taken-
first I'm trying to find that where did I lose it? Yeah, here. Okay. Okay. Exactly your point. So with this 8 to 80, 8 to 80 এর মধ্যে ধরে নেওয়া যাক যে ট্রু আননোন মিন মিউ সেটা হচ্ছে 10
10।
ধরে নেওয়া যাক। তো 8 to 80 এর মধ্যে 10 আছে, 7 to 12 এর মধ্যেও 10 আছে, কোনটাই ভুল না, ও তার রাইট ইন টার্মস অফ the confidence intervals. But 8 to 80, I will say, is less useful for me because it is with so much dispersion, so much variation. I will say, well, 8 ও থাকতে পারে, 10 ও থাকতে পারে, 50 ও থাকতে পারে, 60 ও থাকতে পারে। Whereas এটা এতটা টাইট, তার মানে কি? I mean, I have much more confidence that ওটা মানে 10 মানে ওটা I have got it well.
কিন্তু
না,
এর
এটার মানে কিন্তু আমি প্রথমটা কেসে স্যাম্পলিং ঠিক করে করি বলে আমি এতটা ভেরিয়েবিলিটি পাই না।
হতে পারে বা স্যাম্পল সাইজ
প্রথমে স্যাম্পল সাইজটা কম ছিল
কিন্তু ম্যাথমেটিক্যালি যে বললো যে 8 to 80,
হ্যাঁ।
তাহলে সেক্ষেত্রে আমি যদি বারবার টেস্টটা অন্যান্য স্যাম্পলকে রিপিট করি, তাহলে কি আমার ভ্যালুটা 80 পর্যন্ত যেতে পারে নাকি 12 পর্যন্ত যাবে?
না না আমি
একটা এক্সট্রা
হ্যাঁ
আমি যদি ওই স্যাম্পল সাইজই রেস্ট্রিক্ট করে আমি যদি 100 বার করি
তাহলে
কোনো একবারে ওখান থেকে আসতে পর্যন্ত যাওয়ার চান্স আছে।
So, like as you said, my confidence interval is 95% confidence interval means that there is 95% chance the population mean will fall with that confidence. Am I right?
there are repeated samples repeated samples একবার বলে 95 বার ওইটা
So can it happen that my confidence interval is very narrow, my study is very precise, but I'm actually missing the population.
still could কারণ 95% you equal for the unlucky of the 5 তাহলে হতেই পারে, কিন্তু যখন অতটা প্রিসিশন বেড়ে যাচ্ছে তার মানে your level of confidence is also very high. সেটা 95 না, তখন 99 হ্যাঁ না
99 হচ্ছে বাট একবার আমরা ওই এক্সট্রা করতে পারছি।
করতে পারি আমি ওই 100 জনের মধ্যে একটা যে আনলাকি
সেটা
সেটা আমার কনফিডেন্স হচ্ছে no because you don't know what the unknown is. His confidence is Yes, okay, so is confidence interval related with the mean value? So this is again a fundamental question. We are talking, and again, if you are comfortable with it, I am absolutely comfortable with it. I don't have to go by slides and so let me answer that question. I was may have gone to it, was going to go to it, but I will sort of answer it now. Okay, একটু সিকোয়েন্স বদল করে কাস্টমাইজ করে improvise করে নেই বলা উচিত। আচ্ছা, the question was is confidence interval related to p value, তাই তো? এই ছিল তো প্রশ্নটা। আচ্ছা, এবার এই এক্সাম্পলটা দিয়ে বলি। ডক্টর কৌশিক বলছিলেন যে দুটো let's say now I change your scenario a little. You have two groups, and you have you are saying that I'm going to make it very simple. I want to compare the average BMI in men versus women. ভীষণ বাকি একটা simple problem, right? I want to compare the mean BMI between males and females. Okay, so now there are two ways you can do it. Statistical inference Onujai, there are two ways you can do it. I'll just put the slide on the so there are two ways you can do it. One is you can construct a confidence interval. আরেকটা হচ্ছে you do it as a test of hypothesis. You start with a null hypothesis that the mean BMI in men is equal to the mean BMI in women. That is your null hypothesis. Versus an alternative that the mean BMI in men is not equal to the mean BMI in women. At this point, let's keep it what we call a two-sided alternative. মানে বেশিও হতে পারে আবার কমও হতে পারে। So let's say these are the two ways you can answer your question. Answer this question. একটা হচ্ছে একটা confidence interval you construct with the confidence interval of what the difference in mean between men and women. তার একটা confidence interval. আরেকটা হচ্ছে এই test of. Now how are they related? I'd say যে confidence interval না বলে confidence interval বলাটা better. জার্নাল আর্টিকেলে ছিল কারণ confidence interval packs more information. It so turns out that if you do the hypothesis test and let's say you end up having a p-value of, I'm going to make it up, of 0.3. So what does the p-value of 0.3 mean? The p-value of 0.3 means there is a 30% chance that even if the null hypothesis was true, which is that there is no difference, that you could get a result like this or more extreme. This is quite likely to happen, even if the means were the same. So a p-value of 0.3 means you will not reject the null hypothesis, and you will conclude that there is no statistical evidence to believe that the mean BMI is different between males and females. Right? It's a conclusion based on the hypothesis. And lo and behold, if you construct the confidence interval on the difference in the mean BMI between males and females, you will see that that confidence interval will contain 0 in the interval. So it will go to a negative number to a positive number. তার মানে কি কনফিডেন্স ইন্টারভ্যালটা কি বলছে 95% কনফিডেন্স ইন্টারভ্যালটা বলছে যে it is plausible that 0 is a value in that interval 95 of the times out of 100 times. So I'm pretty I can be pretty confident that 0 is in that confidence interval, 0 is in that interval. 0 interval থাকা মানে 0 হচ্ছে there is the mean BMI of males minus mean BMI of females equal to 0 1 equal. So both will give the exact same conclusion. That's how they are related. But this only works if your alternative hypothesis is two-sided. বেশিও হতে পারে মহিলাদের বা কমও হতে পারে তাদের only works if it's two-sided, but most of the times we are doing two-sided tests. Two-sided alternate. So there the confidence interval and hypothesis test results will be exactly the same equivalent. And that's why I said with the p-value what happens? You give a single number and if they will reject, do not reject, it's far less information packed than a confidence interval because confidence interval tells you the exact same thing, whether you can reject or not reject, but it also gives you kind of the range of answer variability test. Make sense? You are still not active. Do you have other?
I would strike the.
No, I was asking her. No, no, I was always there. Good.
Like as you said, this only goes to if it's a two-sided. It's a one-sided.
If it's a one-sided alternative, this balance doesn't. Then এই যে আমি বললাম যে কনফিডেন্স ইন্টারভ্যালও দেখতে পারো আবার মানে টেস্ট অফ হাইপোথিসিস এর p ভ্যালুও দেখাতে ডাজন্ট ম্যাটার এই ইকুইভ্যালেন্সটা ডাজন্ট
মানে ক্লিয়ারটা কি ওয়ান সাইডেড হয়ে যায় বলে তার জন্য মানে
হ্যাঁ
এটা কম থাকে
হ্যাঁ আলফা রেজিস্টার যেটা হয় ওই টেস্টটা টেস্ট আই এম ডুইং এট আলফা এট 5% আলফা হচ্ছে যে টাইপ 1 এর একটা we were coming to that সেটার ইকুইভ্যালেন্স যেটা হোল্ড করে 95% কনফিডেন্স ইন্টারভ্যাল কিন্তু ওয়ান সাইডেড হয়ে গেলে তখন অ্যালফাটা তো জাস্ট অ্যাগ্রিগেট তখন আমি ওটাকে সিমেট্রিক্যালি দুদিকে ভাগ করতে পারছি না আমরা এটা বুঝছি না আচ্ছা আলফাটা বোঝার কথা না কারণ আলফাটা আসছিল পরে হ্যাঁ সেই জন্য আমি বললাম তো যে আই এম ওকে ইফ আই এম সর্ট অফ একটুখানি কাস্টমাইজ করছি কিন্তু আলফাটা পরে আসছে আচ্ছা আচ্ছা summary statistics so we were actually talking about confidence intervals summary statistics confidence intervals let's say আমি একটা ড্রাগের রেসপন্স রেট I am trying to estimate so I can get a point estimate but my point is confidence interval actually gives you a range of population response rates that are plausible or consistent with the sample data. So here is a little thought experiment. Catching the real response rate. What do I mean by real response rate? That unknown population parameter. Population a response rate ta ki? It's unknown. So I'm trying to catch it. ওই বাটারফ্লাই ঘুরে বেড়াচ্ছের মতো মানে অ্যানালজি আচ্ছা এবার সাপোজ দ্য রিয়েল রেসপন্স রেট ফর আ নিউ থেরাপি ইজ 30%, 0.3. Suppose we run a small safety and efficacy clinical trial and calculate the response rate and a 95% confidence interval for the response rate. What is the big sort of important over and over and over again? So that's the repeated sampling idea. Okay, suppose we do that. Acha, ebar the question is how often will the interval capture the real value? যেটা আমরা কথা বলছিলাম এত 5 বার আমরা মিস করব কে কোন কার এটা মিস করছি আমি জানি না 5 বার মিস করব হ্যাঁ okay so this is sort of the pictorial response how do I get this out I don't
Task further. Can keep the screen.
um
ওইটাতে একটু সরিয়ে সরিয়ে দেবে, ওই কাজ করে।
Hide floating এইটা তো okay
তো
okay so suppose the true rate is 0.3 30% n মানে sample size হচ্ছে 30 আর confidence level হচ্ছে 95%. আমি ওই sample of size 30 নিয়ে বারবার over and over and over again sampling করে আমি confidence interval বার করেছি. আচ্ছা 0.3 হচ্ছে এইখানে, হ্যাঁ ঠিক আছে. Observed rate on the y axis, number of trials মানে ওই repeated sampling 100 বার করছি তো, একবার দুবার তিনবার সেম পপুলেশন থেকে নিয়ে 100 times. So the first time I do it, basically I get a estimated response rate of about 0.2. ঠিক আছে. Next time I do it, আবার এটা freeze করে গেছে. Okay. Yeah, না পেরেছি. Okay. So it's 0.2, are based again on my standard deviation for my sample. I can get a confidence interval. Okay. এবার আমি এটা 5 বার করলাম. তো সেকেন্ড বারও আমি একটা 0.2 কাছাকাছি পেলাম, তারপর আমি পেলাম 0.38, তারপর আবার পেলাম 0.2, এরকম চললো. আচ্ছা ফিফথ বার যখন আমি করলাম স্যাম্পল নিয়ে সেম পপুলেশনটা থেকে, my point estimate of the response rate is 0.6, the black square, and I construct a confidence interval. Okay, do you see where that black square is coming from? Let me just show you. So এটা 5 বার করেছি. আচ্ছা এবার বারবার করে যাচ্ছি, repeated sampling. Okay, so what are those black boxes? Those are the 5 times that I missed the 0.3 true response rate. Oh, sorry. আমার স্ক্রিনে এই যে, so আমি তো 100টা করেছি, প্রত্যেকবার আমার নিজের স্যাম্পলের উপর নিয়ে response rate I estimated and I calculated the confidence interval. So these are the series of confidence intervals like yours that you got. And for some reason, Kiran got this. Okay. So Kiran actually is one of the 5 who missed the true response rate, the 0.3. All the others here, and this guy also missed, this guy missed. So out of the 100, 5 times it did not catch the unknown true response rate of 30%. But 95% of the times it caught.
Here this true response rate is known from that.
No, it's not known. আমি এটা hypothetically বললাম. So usually you don't know.
But in practical scenario তে আমরা যখন জানবো না তখন
তখনও তো the confidence interval এর conceptটা তো still holds. That in repeated sample, that's what gives you confidence যে 95, I am 95% confident that this interval captures the true meaning. That's where your level of confidence is coming. আচ্ছা এবারে একটা প্রশ্ন করি, I have it on my next slide. So everybody clear on this? Okay, now suppose what happens if we want to be more confident. আমি বলছি 95% confidence এ আমি খুশি নই, I want to be 99% confident. Okay, so the true rate is still 0.3. Let's say again hypothetically, আমি কিন্তু জানি না usually. It's 30%. N is still 30 sample size, but the confidence I want to be 99.9% confident. Acha, I am going to show you the series of confidence intervals like in the previous slide. But before I show you that, can you take a guess? Will the confidence intervals be wider or smaller? Will the confidence intervals be wider or
more confidence.
interval should be smaller? Again, I said there is no free lunch. আমি confident হতে চাইবো, either আমার sample size বাড়াতে হবে if I want to retain the same kind of weight, or if I'm not ready to increase the sample size, আমার তাহলে
confidence বাড়াতে যাতে ওটা চলে আসে।
okay, so do you see what happened? So আমি এখন more confident, হ্যাঁ, কিন্তু আমাকে তো কিছু একটা দিতে হবে, মানে you have to give something, get something, right? So intermediate length হলো হয়ে গেছে। Make sense? So the one thing you could say, like, I kept the sample size to be 30, মানে আমি sample size ও বাড়াবো না, আমার 30 দিয়েই কাজ চালাতে হবে আমাকে, but I want to be more big, I want to be 99% confident. So then you have to give up something, you have to give up on the precision a little bit, and that's exactly what is happening. See, like all the intervals actually now capture 0.3, the true response rate. Current 0.1%, তো আমি তো 99.9, so সবাই 100টাই মানে captured the true response rate. But I compromised on the precision. Now it's wider. What happens if we want to be 95% confidence, but we increase the sample size? এইবার কি হবে? Smaller হবে। কারণ I'm giving something, I'm using more resources. So the true rate is still 30%. My sample size now, instead of 30, I have 4 times sample size, 30%. আমি একটা চা নিয়ে নেব সেখান থেকে।
If I increase the sample size, the precise so have interval of confidence.
হ্যাঁ,
This is a better option.
হ্যাঁ, better option if you have the resources. Sometimes you don't have some sample size, yes, but sometimes you don't have the resources, you cannot afford the cost, right? So this is what happens. Now do you see? So the true rate is still 30%. I mean, the sample size now I have made it 4-fold, and do you see, like, I actually have essentially still there are 5 reds, I have missed 5 times, into all the intervals are much narrower. In other words, more precise estimate. That's what happens. Okay. So statistical inference, as I said, there are like 2 ways you can do it. One through confidence intervals and another through the hypothesis test framework. So let's talk about the hypothesis test frameworks. And you said, where is this alpha coming from? So alpha ever আসছে. We kind of jumped a little bit and we talked about the equivalence of confidence intervals and hypothesis tests, but this is the essence of statistical hypothesis testing. So making decisions, test of hypothesis, there is a null hypothesis that there is no difference between smokers and non-smokers. Let's say our alternative hypothesis is the researcher's theory. Let's say the researcher's theory is that he or she wants to prove that tell me something that, I mean, there are so many things that smoking that it's hard to just be. So, like, let's say there's the researcher's hypothesis is that there's a difference between smokers and non-smokers in life in years. Lung disease. Some biomarker of lung injury, let's say, continuous biomarker of lung injury. So that's the researcher's theory. So now, test of hypothesis often is compared to like a court trial, jury trial. So the thing is that there is nature, or that is throwing in all sorts of random noise, error, and making up things. So if you compare the mean biomarker value of lung impairment in smokers versus non-smokers, and if the truth is the null hypothesis, meaning there is no difference, And then there is a table that I have. So the columns of the table is what is the truth. And truth হচ্ছে either H naught is true or H naught is not true. মানে H naught true মানে হচ্ছে there is no difference between smokers and non-smokers. আর H naught not true মানে হচ্ছে there is difference. So in the columns what I have are the truth. And in the rows what I have are my decisions. Based on data, do I accept the null hypothesis or do I reject the null hypothesis? এইটা মনে রাখতে হবে। রোতে হচ্ছে ডিসিশনস আর কলাম গুলো হচ্ছে the truth. আচ্ছা, if I now make a 2x2 table of this, if the null hypothesis is true and I accept the null hypothesis, then I'm happy because I have made the right decision. If the null hypothesis is not true and I have ended up rejecting the null hypothesis, then also I am happy, right? Because I have made the correct decision. কিন্তু গন্ডগোল হবে if I am on this like the other off diagonal. যদি এরকম হয় যে the null hypothesis is true and I ended up rejecting null saying that there is a difference between smokers and non-smokers, তাহলে I'll be unhappy. So I have a sad, grumpy face here. Also, if the, let me come to that, let me finish the other part. So if the null hypothesis is not true, meaning that there is a difference between smokers and non-smokers, but I say that accept H naught, মানে say that there is no difference, তাহলেও I will be unhappy because I have made a wrong decision. So these are the two scenarios when I will be upset, I will be unhappy because I have made incorrect decisions. This error here is called the type 1 error, the alpha. This is the alpha guy. So basically, I am saying that's an error, that alpha, which I want to minimize. I want to make it as small as possible. There is this other type of error when H naught is not true, but I end up accepting H naught. That is also a bad decision. That is called a type 2 error. 1 minus, no, that is beta, and power is 1 minus. Okay, so now this is a slide ta bujhle you can understand hypothesis testing. So these are the two different types of error. So now ideally, this is what happens. We call, আপনি জিজ্ঞেস করছিলেন alpha কি? Alpha is this guy. It is the probability of making a type 1 error. This is also called the level of significance. Okay. And beta is the probability of type 2 error. This is also a bad decision. Okay, so that's beta. Eibar, now tell me something. If I could have any wish with Bhute Raja bor deoar moto, I say, okay, Bhute Raja bor dilo, go and take your wish. Ideally, what would I want? I would want both alpha and beta to be very small, right? And I mean, কোনোটাতেই error করতে রাজি। Yes, everybody agrees. কিন্তু in real life সব পাওয়া যায় না। So সেই কারণে যেটা হয় যে একটা বাড়ালে আরেকটা simultaneously কমতে থাকে, আবার একটা কমালে আরেকটা simultaneously বাড়তে থাকে। That's the sort of the dynamics between the alpha and the beta, between these two types of things. So convention অনুযায়ী কি করা হয়? Usually the type 1 error is a more serious error because you are saying reject the null hypothesis when the null hypothesis is true. Okay. So, you are saying that two drugs, the new drug and the control drug have different efficacy, when actually there is no difference between the two drugs. So that is usually by convention a more serious error. It doesn't have to be always, but because that is a more serious error, you say, I am not willing to make more than 5% error on the type 1. Therein the 5% level of significance comes from. আমরা অনেক সময় ভাবি না যে 5% সবাই 5% use করে. What is so holy about 5%? But the 5% comes from that. You are saying that the type 1 error is more serious than the type 2 error. So I am not willing to commit more than 5% error in type 1. So once you fix the type 1 error at the level of significance at 5%, then your goal is keeping that fixed at 5%, how much you can minimize the beta. Power is related to that. Power is the probability of rejecting the null hypothesis when actually the null hypothesis does not hold. So you are making a correct decision. So এবার beta হচ্ছে 1 minus power or power is 1 minus beta. এবার আমি যদি ওই টাইপ 1 এররটাকে 5% এ রেখে বেটাটাকে যতটা সম্ভব ছোট করতে পারি, তার মানে কি আমি পাওয়ারটাকে যতটা সম্ভব বড় করতে পারি? So that's the ideal situation for me. I am saying that, look, if I can afford to, again, sample size most of the time it turns out to be the sample size. If I can recruit 200 patients in my study, then I can make my type 1 error, keeping type 1 error fixed at 5%. I will still actually have 90% power, meaning that 90% of the time I will make a correct decision when I'm rejecting the null hypothesis. So that's the whole essence of why we care about power. Because you should ask yourself this question: what is power for me, and why do I care? Why am I chasing power? The reason you are chasing power is power actually gives you it's the probability of making a correct decision. But a correct decision that is important for you. You want to reject the null hypothesis when actually there is a difference. You are saying that the two drugs, compared to the control, the new drug is much better. So 90% power allows you to detect that these confidence and to reject the null hypothesis and say that there is a difference between two drugs.
So, two questions. One is that how do we decide that type 1 error is important or type 2 error is?
Yeah, so that's again a very, very good question. And as I said, conventionally type 1 error টাই সবসময় turns out to be more serious than a type 2 error, but it doesn't always have to be. So I will, to answer your question, here is the analogy. Hypothesis testing এ on কে compare করা হয় jury trial এর সঙ্গে। আচ্ছা, jury trial এ কি, you are presumed innocent unless you are proved guilty, right? So the presumed innocent is the null hypothesis in the statistical test, and guilty is the alternative hypothesis. So in statistical hypothesis testing, you are saying that, show me the evidence that the new drug is better than the old drug. Otherwise, I'm going to presume that there is no difference. So the onus is on you as a researcher to prove to me. Same as prove first guilty, otherwise I'll assume innocent. The level of significance is the reasonable doubt. Beyond reasonable doubt, I have to So if you are correctly rejecting the null hypothesis, you are convicting a felon. Good. If you are correctly accepting the null hypothesis, you are acquitting the innocent. What is the meaning of type 1 error in the jury trial? You are rejecting the null hypothesis given the null hypothesis is true. Rejecting the null hypothesis mane hocche you are saying a person is guilty, but actually the person was innocent. And a type 2 error is you are acquitting a felon. So the analogy, and in most cases, like that's how you frame your hypothesis test. You are saying that convicting an innocent is a far serious error than letting a felon out. Again, society might put different kinds of perspectives in, but that's the usual norm. So
And the other thing was that if you go back to the slide, the previous slide about the sample set. So I couldn't understand that how is power related to sample size?
oh yeah, so power I showed it to you in terms of all like the probability of type 1 and type 2 error. So power, how is it a function of, okay, I also had a slide about clinical trial. Maybe I'll quickly go to that and then come to the sample size. So in your situation, like more relevant, hypothesis testing and drug trials. Again, you will start with the drug is useless, new drug, and you have the onus is on you to prove that the new drug is effective. So correctly rejecting the null hypothesis is you are keeping an effective drug. And correctly accepting the null hypothesis is you are abandoning a useless drug. What is the type 1 error? You are essentially keeping a useless drug. And a type 2 error is you are abandoning a effective drug. So if you are keeping a useless drug based on your hypothesis test, you are marketing it, that's a far like serious error. So because FDA has to regulate in the US, the Food and Drug Administration has to regulate all drugs that go out in the market. And based on your hypothesis test, if they're bringing in the market a useless drug, that is a far serious error than abandoning an effective drug. So the type 1 error is the much more serious error. So now coming to your question about the sample size. So the study paradigm goes like this. You first set up your hypothesis, you design the study, you conduct study, collect data, examine data, then you decide, you compute the test statistic, compare to null distribution, compute p-value, reject if p is less than alpha, etc. Eibar, I'm just trying to think. We have less than 5 minutes. I want to come to your question. This was an example of a test of hypothesis where I wanted to compare the rate of new breast cancers in tamoxifen treated and placebo treated subjects over 5 years. So here is a 2x2 table showing the data, and this is hypothetical data. But the point that I want to make is that this is based on a chi-square test, which we will see tomorrow. And the p-value for this, based on the chi-square distribution, was basically this is where the test statistic fell 3.84 with a p-value of 0.05. And if the test statistic is 6.65, it's a 0.01. So anyway, the whole point about this slide was that based on the p-value, you can make the conclusion. Now, I will skip these slides in the interest of time. We can come back to it tomorrow because we are talking about categorical data tomorrow anyway. Now, let's talk about how is power related to sample size, or even test of significance related to sample size. So here, I did the same study with a total sample size of 2000. এই হচ্ছে আমার নাম্বারটা, টোটাল 2000, তার মধ্যে tamoxifen পেয়েছে 1000, placebo পেয়েছে 1000. And the p-value from this is a 0.01. Now, what I do is the exact same question আমি sample size টাকে double করে দিয়েছি হ্যাঁ I made the total sample size 4000 2000 2000 in each group. Now do you see what happened to the p-value? The test statistic also became twofold and the p-value is less than 0.005, like it's much more significant than this one. Qualitatively, the evidence in terms of the response, the breast cancer rate is the same. The point estimate is the same, but the p-value becomes like different. One becomes much more statistically significant than other. Why? Because I have increased the sample size by twofold. So same rate, আবার ওই একই জিনিস, same point estimate, কিন্তু based on a sample of 2000 versus a sample of 4000 makes the evidence much more compelling.
নাকি আমার question ছিল,
আমি বাসছি
ওখান থেকে আমরা কি
ওখান থেকে না, কারণ বেটাটার মধ্যেও তো স্যাম্পল সাইজ আছে। আমি আসছি আপনার প্রশ্নটাতে আসছি, কারণ আপনি আচ্ছা পি ভ্যালুটা আমি বুঝে গেছি, রাইট? ইফ হাউ কনসিস্টেন্ট অর ইনকনসিস্টেন্ট আর দ্য অবজার্ভ ডেটা। এইবার আমি পাওয়ারে আসি, কারণ এগুলো we have to skip. So these are p values are and confidence intervals. I'm going to just skip this. Okay, sample size power. Power হচ্ছে 1 minus beta. It estimates the power to detect a specified difference given a particular sample size. এইবার ওই বেটাটার মধ্যেও, কারণ বেটাটার মধ্যেও তো টেস্ট স্ট্যাটিস্টিকটা আছে and there is a sample size there. The power tells us how likely it is that a significant difference will be found given that the alternative is true. And we all know that we don't like power to be low, because if power is too low, there is little chance of finding a significant difference and non-significant results are likely, even if there are real differences. So what is the relationship between power and sample size? That's the question you were asking. It turns out that power and sample size relationships are quadratic. Usually, যখন low power দেখা যাচ্ছে to detect a scientifically meaningful difference, usually it's the sample size. So this is where clinical significance versus statistical significance also comes into play. And here are the building blocks of power. So, you know, there is a test statistic. This is the sample size. This is, I'm talking about two groups or multiple groups, imbalance in size of groups. This delta is the effect size. Alpha is type 1 error, beta is type 2 error, and power is 1 minus beta. But the relationship, there are other considerations also. There are, you know, censoring, adjusting for confounding, correlations among variables, and this is the relationship between the ingredients. So if we simply look at power, sample size, sample size is one big consideration. Kintu there may be other considerations also. If we increase the sample size, n has a up arrow, then power, what happens to power? All other things remain the same. Alpha same, delta same, imbalance same. Then the power will increase. Okay. What happens to sorry. So that is the relationship. So essentially, everything you have to interpret it to say everything remaining the same. Power is a function of the sample size. So the relationship, এটা অন্যভাবেও if you want to interpret the table, the relationship between sample size and alpha level. So if you increase n, the significance level will decrease if you kept the power constant. And the way to read this is all the other things are left constant. Definitely, কারণ পাওয়ারটা আমি 80% এই রাখছি, আমি স্যাম্পল সাইজে ইনক্রিজ করছি, সুতরাং আমি কি পাবো, আমার টাইপ 1 এররটা আরেকটু কমে যাবে। If you increase the sample size, but you kept the type 1 error to be fixed, the alpha to be fixed at 5%, the effect size is Dr. China probably what we were also talking about. We did 3.8 পেলাম না হয় effect size across studies, যেখানে 2000 টা ছিল versus 4000 টা ছিল। 3.8 is the same estimate, but with a sample size of 4000, I get more power to detect that. So that's the other thing I want to point out your attention to, because a lot of times this happens when you are doing sample size calculations for a grant, let's say. You're trying to design a study and you have limited resources. You say, I want to have my 5% type 1 error, and I want to have at least 80% power to detect a certain difference. Right? So I come back and you come back and tell me that, I don't have enough money, budget to recruit more than 500 patients. তখন the struggle becomes, then I come and tell you, well, if you cannot recruit more than 500 patients, I still want 8% power, তাহলে you may have to settle with an effect size, let's say in the logistic model, you may have to settle with a clinical difference of 20%. Now 20% clinical difference can be huge for you. And you might say 20% difference আমি কোনোদিনই পাবো না, মানে কতটা different response rate হবে না। Then that's when the sort of the interplay between power, sample size, type 1 error all comes into play. So it's always a complex math optimization between sample size, power, between effect size, the power and sample size, what you can add. So if you say, for me, a clinically meaningful difference is 10%, and I can only recruit 500 patients, then again, depending on sort of the parameters, different considerations of the model, if you're adjusting for a lot of confounders, etc., then basically I tell you, well, with 500 patients, to detect a 10% difference as statistically significant, you will only have 70% power. Whereas if you are willing to say that, okay, 10% clinical difference now, I can probably live with a 15% clinical difference. To detect a larger difference, you will need a smaller sample size. So that's the essence. That's the okay. So I think I will stop here because thank you for staying. Did you want? Huh?
Maybe for each variable, I will no,
The first thing, everything evolves around that. What is primary goal? Understand the application, certain is ready. What is the primary predictor? What is the primary exposure? Oftentimes, I don't know, for a clinical trial question, there's a drug, there's an interval. You want to test for the effect. but you want to adjust for many other things. So then you have to let the study objective guide the analysis. Sure, my next
You can just start on a culture again.
We will conclude here. So we have enriching and great sessions coming up tomorrow. So we will join back again morning at 11 a.m. So thank you.
Okay, thank you. আচ্ছা এটা আমি বেরিয়ে যাব তো লিভ শুড আই লিভ
Ah, yes.